Hello and welcome to this revision session for AQA A-Level Physics, Paper 1, looking at the topic of waves and the concept of progressive waves. So in today's revision session, if we've been successful and we've learned today, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when you're completing your revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side. And in this left hand side section, what you should be doing is writing down your working out and answers to the questions in this revision session. And when you're doing this, make sure you write your answers in full sentences and show your full working out. Whilst on the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, you should write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes and a knowledge checker to learn the key ideas of the course. Now you may wish to make mind maps or to write out the notes yourself. Secondly, test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then use exam prep books, homework books, study books and additional workbooks to answer exam questions and to mark your own work. Now you may wish to download your own exam past papers to do this. So your 3 steps of learn the key facts, testing yourself and practicing exam style questions are how you can prepare for your A-Level Physics examination. So let's have a look at what questions we're going to be using in our papers today. There'll be 2 types of questions we want to use. Firstly, general checker questions, basic questions designed to probe your understanding of the key concepts of the topic. Then we'll be looking at assessment point questions. These are past paper examination questions which will mimic the types of questions found in public examinations. So let's start with our general checker questions. What type of wave is this and how can you tell? So pause the video now, then unpause the video when you want to go through your answer. Well, this wave is a progressive wave. As energy is being transferred, the wave is a transverse wave as the propagation is at right angles to the oscillation. In which direction is the particle at A moving? Pause the video now, then unpause the video when you want to go through your answer. By reviewing the wave pattern and how the wave pattern is moving across the particles, you can see that the particle at A will be moving downwards. The next question, in which direction is the particle at B moving? So pause the video now, then unpause the video when you want to go through your answer. Again, by looking at how the wave pattern is moving, the particle at B will be moving upwards. The next question, what is the amplitude of this wave? Pause the video now, then unpause the video when you want to go through your answer. Again, you've got to understand the definition of amplitude. Amplitude is from equilibrium to the peak or the trough of the wave, so it's half of 7.50, 3.75 millimeters. Figure 7 shows a continuous progressive wave on a rope. There is a knot in the rope, the wave travels to the right. Describe how the vertical displacement of the knot varies over the complete cycle. So pause the video now, then unpause the video when you want to go through your answer. Once again, you've got to imagine the wave pattern travelling through the particles and causing them to oscillate. So it will go vertically downwards, so it will be a quarter cycle to the maximum negative displacement, then upwards again, a quarter of a cycle back to equilibrium, then another quarter of the cycle back to positive displacement, and then back down again, so another quarter of the cycle to equilibrium position or zero displacement. Now, the continuous wave of the same amplitude and frequency moves along the rope from the right and passes through the first wave. The knot becomes motionless. Explain how this could happen. So pause the video now, then unpause the video when you want to go through your answer. Well, a stationary wave will have been formed by superposition or interference of the 2 coherent progressive waves. Now the knot must be sat at a node, as the waves will always cancel where you've got the knot and there's node. Okay, so there's a node displacement and no oscillation there. Figure 6 represents a progressive wave travelling from the left to the right on a stretched string. Calculate the wavelength of the wave. So pause the video now, then unpause the video when you want to go through your answer. You should identify that the distance of 0.50 meters represents 1 1/4 waves. So 1 1/4 of 0.5 will equal us to be 0.40 meters. The frequency of the wave is 22 Hz. Calculate the speed of the wave. So pause the video now, then unpause the video when you want to go through your answer. So, how do you work out the speed? The speed is equal to frequency times by wavelength. So it's 22 times by 0.40, that's the wavelength of the wave, which equals 8.8 meters per second. On this wave, describe how the displacement of point Y on the string varies in the next half period. So pause the video now, then unpause the video when you want to go through your answer. Now again, you've got to imagine the wave pattern travelling through the particles as it moves across in the direction of the wave travel. So what you can see is that position Y, it'll be at a position of maximum, at a quarter of the period or the cycle, and then it'll return back to its original position in the next half period. You can see that it's going to be moving upwards because you can see that the maximum is pushing upwards on that particular wave pattern there. Next question says, what is the path difference between points A and C? So pause the video now and then unpause the video when you want to go through your answer. So that's going to be half a wavelength because you can see A and C are separated by half a wavelength, okay, when you look at your wave pattern. So what is the path difference between A and D? So pause the video now and then unpause the video when you want to go through your answer. Right, so our answer here is going to be 0.75 wavelengths. Next question, what is the path difference between points E and K? So pause the video now and then unpause the video when you want to go through your answer. Our answer is either 1.5 wavelengths, or you would say half a wavelength, because it can reset after a wavelength because the overall displacement from the initial is half a wavelength. What is the path difference between D and L? So pause the video now and then unpause the video when you want to go through your answer. Right, the answer is 2 wavelengths or 1 wavelength. The next question says, what is the path difference between C and J? So pause the video now and then unpause the video when you want to go through your answer. It will be 1 3/4 wavelengths or 3/4 wavelength. What is the phase difference between point A and E in degrees? So pause the video now, then unpause the video when you want to go through your answer. The answer is 360 degrees, as it's one whole wavelength between the two, but also it could be interpreted as 0 degrees because it resets after every wavelength. What is the phase difference between points B and K in degrees? So pause the video now and then unpause the video when you want to go through your answer. The answer is either 810 degrees, or if you reset after every 360 degrees, 90 degrees. What is the phase difference between points F and L in degrees? Pause the video now and then unpause the video when you want to go through your answer. The answer is either 540 degrees or 180 degrees. The next question says, what is the phase difference between points C and H in degrees? So pause the video now and then unpause the video when you want to go through your answer. The answer is 450 degrees or 90 degrees. What is the phase difference between points D and I in degrees? Pause the video now, then unpause the video when you want to go through your answer. The answer is 450 degrees or 90 degrees. What is the phase difference between points A and D in radians? Pause the video now, then unpause the video when you want to go through your answer. The answer is 1 3/4 pi radians. Now remember, there are 2 pi radians in every wave cycle. So between A and D, which is going to be 3/4 of a wave, we can therefore see that it's going to be 1 3/4 pi radians. What is the phase difference between A and E in radians? So pause the video now, then unpause the video when you want to go through your answer. The answer is 2 pi radians or 0 pi radians because it resets after every 2 pi radians. What is the phase difference between B and F in radians? The answer is 2 pi radians or 0 pi radians. What is the phase difference between points E and G in radians? When you look on here, it's going to be half a wavelength, so that's 1 pi radians. What is the phase difference between points E and L in radians? Pause the video now, then unpause the video when you want to go through your answer. The answer is 1 3/4 radians. The next question says, what is the phase difference between points A and M in radians? So pause the video now and unpause the video when you want to go through your answer. The answer is either 6 pi radians, 2 pi radians, or 0 pi radians. What is the phase difference between points C and I in radians? So pause the video now, then unpause the video when you want to go through your answer. The answer is either 3 pi radians or 1 pi radian. The next question says, the light incident on the camera lens is unpolarized. The photographer places a polarizing filter in front of a lens. Explain how the polarizing filter affects the light incident on the camera lens. So pause the video now, then unpause the video when you want to go through your answer. Well, when we look at this answer, unpolarized light oscillates in many different planes. Now, the light perpendicular to the plane polarization of the filter is absorbed, or only the light parallel to the plane of polarization of the filter is transmitted. So this tells us that the polarized light will only oscillate in one plane, so therefore our light intensity is reduced. The next question says, state what is meant by unpolarized light and describe how you can determine using a polarizing filter whether a light source is giving out polarized or unpolarized light. So pause the video now, then unpause the video when you want to go through your answer. Now, in unpolarized light, vibrations are in all directions, at right angles to the direction of travel, and the sequence of directions is random. Now, to distinguish this, viewing light through a Polaroid and rotating it can be used. So light is unpolarized if the intensity doesn't depend on the angle of the Polaroid. Now, light is polarized if it does depend on the angle of the Polaroid. The Polaroid will decrease the intensity of the unpolarized light, so for polarized light there are two angles of extinction per turn of the Polaroid. They tend to be when it's going to be at 90 degrees and 270 degrees. Next question, explain why sound waves cannot be polarized. So pause the video now, then unpause the video when you want to go through your answer. So sound waves are longitudinal waves. So since oscillations are parallel or the same direction to wave travel, it tells us that they cannot be polarized. Next question, explain why polarized sunglasses will help find a person fishing to see fish more clearly. So pause the video now, then unpause the video when you want to go through your answer. Reflected light is polarized, so the intensity of light reflected on the water will be reduced by the polarizing filter. The next question says, figure 2 shows the displacement of a string as the wave travels along the string. Give the amplitude of the wave. Give the wavelength of the wave, and a different transverse wave has a wavelength of 1.8 meters and a frequency of 16 Hz. Calculate the speed of this wave. So pause the video now, then unpause the video when you want to go through your answer. So the amplitude is from equilibrium to the peak or the trough, so that will be 19 centimeters. The wavelength is the length of one whole cycle, which is 80 centimeters. And the speed of this wave is going to be frequency times by wavelength, 16 times by 1.8, 29.0 meters per second. The next question says, figure 1 shows the displacement of a surface water wave with time. Identify the number of oscillations shown in figure 1. Give the amplitude of the surface water wave shown in figure 1 and give the period of the surface water wave shown in figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, how many oscillations do we have in figure 1? Well, you can see the wave pattern is repeated 2.5 times. The amplitude is from equilibrium to the peak, which is going to be 8 centimeters, and our period is the time taken for one whole complete wave, which is 20 seconds. A student is wearing polarizing sunglasses observes a mobile phone screen. The student rotates the mobile phone through 90 degrees as shown. The screen then appears to completely black. Explain why the screen appears completely black when the student rotates the mobile phone through 90 degrees. So, pause the video now, then unpause the video when you want to go through your answer. Right, so what can we say? Well, light emitted from the mobile phone screen is going to be polarized because it's affected by the angle of the Polaroid. So when the phone is rotated, the plane of polarization of the light and the plane of polarization of the polarizing filter in the sunglasses are perpendicular when the phone is rotated, and then the polarizing filter on the sunglasses will absorb the light. So let's now have a look at some examination style questions. So a research group is studying water waves travelling across a still lake. Further observations reveal a wave passes a stationary buoy causing it to oscillate with a period of 1.6 seconds. State what is meant by a progressive wave and describe how the particles of the water move as the wave passes. Determine the wavelength, frequency and speed of the wave. 2 points P and Q are separated by 0.20 meters along the direction of wave travel. Calculate the phase difference between the oscillations of P and Q, expressing your answer in both radians and as a fraction of a full cycle. Then researchers suggest that the energy is transferred by the wave, but that the water itself does not travel across the lake. Explain how the progressive waves transfer energy without the net transfer of matter. So pause the video now, then unpause the video when you want to go through your answer. Okay, in this first question, a progressive wave transfers energy through a medium without transfer material between points. Particles in the medium will oscillate about fixed equilibrium positions, and in a surface water wave, the particles will move in circular or elliptical orbits as the wave passes. Now, the oscillation is going to be local. The waveform moves, not the medium. We can see the wavelength from the diagram. It's 0.80 meters. The time period is given in the question 1.6 seconds. The frequency is 1 over the time period, 1 over 1.6, so 0.625 hertz. The speed is frequency times by wavelength, so therefore it's 0.50 meters per second. Now the difference between P and Q is 0.20 meters. So as a fraction of the wavelength, that's 0.2 over 0.80, so it's 0.25. So therefore the phase difference is a quarter of a full cycle. Now in radians, we know a full cycle is 2 pi radians, so therefore the phase difference is pi over 2 radians. Now particles will oscillate about fixed points, but they don't experience a net movement over a complete cycle. The energy is carried by the oscillations propagating through the medium, not by the movement of the material itself. The next question says a sports science team investigates how water waves behave at a surfing competition. They set up a monitoring station on the beach and record the following data for a series of incoming ocean waves. Later, they measure the speed of the surfers relative to the water as approximately 2.5 meters per second when catching a wave. The team notices that the waves are steeper and break more easily closer to the beach, where the water depth is much shallower. Calculate the speed of the progressive waves as they travel towards the beach. Compare the speed of the waves with the typical speed of the surfer, and discuss whether a surfer will be able to catch and ride the waves based on these speeds. Explain why waves break more easily in shallow water in terms of changes to wave properties such as speed, wavelength and amplitude. Then evaluate 2 practical challenges that the team would face when collecting accurate wave data in a real sporting event at the beach, and suggest how they could minimise these errors. So pause the video now, then unpause the video when you want to go through your answer. Okay, so how do you calculate the wave speed, the speed? So we know that v is going to be equal to lambda over t, so it's 14 over 7, so it's 2.0 meters per second. Now the wave speed is 2 meters per second, the surface speed is 2.5 meters per second relative to the water. So to catch a wave, the surfer must match or exceed the wave speed relative to the ground. Now since the surface speed is greater than the wave speed, they will be able to catch and ride the wave. Now in shallow water, the wave speed decreases because the wave interacts with the seabed. As the speed decreases, the wavelength shortens and the wave height, the amplitude increases. This increased amplitude causes instability, leading the wave to steepen and eventually break. Now in the next one, the variable environmental conditions like the tides and the winds will make the time and distance measurements less reliable. The challenge is that the visual measurements from the shore are subject to parallax errors, to human reaction time errors, so using automatic wave sensors and GPS timing and positioning equipment perpendicular to wave motion will help minimise these errors. A new city communication network is being designed, which will rely on both optical and radio wave technologies. Engineers are discussing the orientation of aerials for radio wave transmission and the use of polarizing filters for optical communication safety systems. During the design meeting, the following claims are made. Claim 1. Polarization does not prove that electromagnetic waves are transverse, because particles in a longitudinal wave could also align in a single plane. Radio wave aerials will transmit equally well regardless of how the transmitting and receiving aerials are aligned. Claim 3. Using polarizing filters with optical signals can help prevent interference from sunlight. So explain why the phenomena of polarization provides strong evidence that electromagnetic waves are transverse in nature. Critically assess Claim 1 made by the engineers. Explain the physical reason why radio wave aerials must be correctly aligned for maximum signal transmission, referencing the properties of electromagnetic waves. Then evaluate the claim about using polarizing filters to reduce interference from sunlight in optical communication systems. So, pause the video now, then unpause the video when you want to go through your answer. Okay, in the first one, polarization involves restricting the oscillations of a wave to a single plane. Now, only transverse waves can have oscillations perpendicular to the direction of energy transfer. Longitudinal waves will oscillate parallel to the direction of energy transfer and therefore cannot be polarized. So, observation of polarization is direct evidence that electromagnetic waves are transverse. Now, claim 1 is incorrect because in longitudinal waves, oscillations will always be along the direction of travel. No transverse oscillation plane will exist for a longitudinal wave, so it can't be restricted by polarization. Therefore, polarization can only indicate transverse oscillation, not longitudinal. Next one, radio waves are electromagnetic waves. The electrical field oscillates in a particular direction. The areals must align with the electrical field oscillations to effectively transmit and receive signals. Misaligned areals result in reduced signal reception or even complete cancellation if there is a misalignment of 90 degrees between the areal and the field. So therefore, the correct orientation is critical for efficient transfer in radio communications. Now, sunlight is largely unpolarized, with electrical fields vibrating in many different random directions. Reflected sunlight often becomes partially polarized, predominantly in the horizontal directions. So our polarizing filters will align vertically, then they can block out much of this horizontally polarized reflections, improving our optical communication signal clarity. So therefore, this claim is correct. Polarizing filters can effectively reduce interference from light sources. During an earthquake, two types of seismic wave are detected by monitoring stations, P waves and S waves. P waves are detected first, followed by S waves a few minutes later. Engineers analysing earthquake data observe the following properties. So the seismologist uses information to help locate the earthquake's epicenter and infer properties about the Earth's interior. So, identify which types of wave, P waves or S waves, is longitudinal, which is transverse. Explain your reasoning with reference to the displacement of particles relative to the direction of wave propagation. Discuss how the difference in speed in P waves and S waves can be used in monitoring stations to estimate the locations of different earthquake epicenters. Then explain, using the nature of wave motions, why the P and S waves arrive at monitoring stations at different times, even though they're generated by the same earthquake event. Then evaluate how the study of seismic waves has contributed to the understanding of the Earth's internal structure compared to early models that assumed the Earth was completely solid. So, pause the video now, then unpause the video when you want to go through your answer. Right, so let's go through the answer to this particular question. Now, P waves have a particle displacement parallel to wave direction, so therefore they're longitudinal. S waves have a particle displacement perpendicular to wave direction, so are transverse. In longitudinal waves, you get compressions and rarefactions occurring along the direction of energy propagation. In transverse waves, oscillations are perpendicular to the direction of energy transfer. Next, P waves travel faster than S waves and therefore arrive earlier at monitoring stations. The time difference between P and S wave arrival increases with distance from the epicenter. Now, by measuring the different time differences at multiple locations and distances from each station can be easily determined. Now, using triangulation from several stations, the epicenter location can be located and calculated accurately. Now, P waves are longitudinal, whereas oscillations are parallel to wave propagation. Now, S waves are transverse, where the oscillations are perpendicular to propagation direction. Now, longitudinal waves typically travel faster through solids than transverse waves. So therefore, the P waves will arrive first, followed by our slower S waves. Now, seismic studies show that S waves stop at the outer core, revealing that they must be a liquid. Now, P wave speeds changes indicate different layers with varying densities and states: solid inner core, liquid outer core, solid mantle. So our modern Earth models recognize layered internal structure rather than the assumption which we earlier had of a completely solid Earth. Now, a physics research team is investigating stationary waves in 3 different experiments. Experiment A, a stretched string fixed at both ends vibrating in different modes. Experiment B, microwaves reflected between 2 parallel metal plates. Sound waves trapped between 2 waves forming an acoustic standing wave. In experiment A, the following measurements are taken for the first harmonic. Explain how stationary waves are formed in each of the 3 experiments. In your answer, refer to the superposition of wave travelling in opposite direction. Sketch a labelled diagram showing the displacement pattern of the string vibrating in the second harmonic. Label all the nodes and antinodes. Using the data for experiment A, calculate the frequency vibrating at the first harmonic. Discuss why in experiment B the maximum electrical field strength is not observed exactly at the metal plates but instead occurs at some distance away. Then evaluate the usefulness of the stationary wave model for describing real sound waves in a room. In your answer, consider the strengths and limitations of the model. So pause the video now, then unpause the video when you want to go through your answer. Right, so in our first one, stationary waves form with two waves which are coherent, so identical frequency, amplitude, and constant phase difference travel in opposite directions and superpose. So on the string, the reflections of fixed end cause the incoming and reflected waves to superimpose, creating nodes and antinodes. In microwaves, the electrical field waves reflect between the metal plates, forming standing electromagnetic waves with nodes and antinodes. In sound waves, the pressure variations of the sound wave reflect off the walls, superposing to form stationary sound patterns of pressure nodes and antinodes. Next question, a correct sketch of a string with a node at each end and one node in the centre with two loops. You label your nodes, your zero displacement points, and your antinodes, your maximum displacement points. It should be symmetrical with half a wavelength fitting between through the nodes, as shown. Now in our next question, we know F is equal to 1 over 2L times by the T over the mass per unit length. So it's a half times by 0.75 over the square root of 20 over 1.2 times 10 to the minus 3, so it's 86.1 Hertz. Now in metal surfaces, the boundary conditions will force the electrical field to be a node, because at the ends of both of the wave pattern there must be nodes. So the maximum field strength, the antinodes, occurs halfway between the nodes, but not at the plates, but at distances corresponding to quarter wavelengths away. So therefore our maximum field is observed in the middle of the cavity, not at the surfaces. Now, stationary wave models can explain things such as resonance, room harmonics, and the standing sound waves that occur at particular frequencies, which leads to acoustics. But in real rooms, walls are not perfect reflectors, and some absorption and scattering can occur, distorting ideal stationary wave patterns. So whilst useful for predicting dominant resonances and the stationary wave model must be adjusted for real-world conditions involving imperfect reflections. A violinist notices an unusual pattern during a concert rehearsal. One of the strings produces a noticeably lower pitch than usual, even though its length appears unchanged. The maintenance technician has checked the string and notes the following. The tension of the string has decreased slightly after transport. The mass per unit length of the string is unchanged. The string is designed to operate in a second harmonic mode during performance. The violin string has a length of 0.35 meters. Later, the technician adjusts the tension back to its intended value and retunes the string. When plucked, the string now vibrates cleanly and a frequency of 440 Hz is detected for the second harmonic. The technician wants to ensure that the first harmonic would correspond correctly to the design specification for the material used. Explain, without calculation, why a decrease in tension will cause the pitch of the string to lower. Use the information provided to determine whether the original first harmonic frequency for the string would meet the design requirement of 220 Hz. Describe the form of the stationary wave pattern when the string vibrates in the second harmonic, clearly indicating the position of nodes and antinodes. Then critically evaluate whether adjusting the string length rather than the tension would have been a better approach for correcting the tuning problem. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first one, lowering the tension reduces the restoring force acting on the displaced particles of the string. The reduced restoring force lowers the speed of the wave propagation along the string. The lower wave speed results in a lower frequency for a fixed wavelength, so you'll get a lower pitch. Now in the second harmonic, we know that it's going to be double the first harmonic. Now given that F2 is 440 Hz, F1, the first harmonic, is 220 Hz. 220 Hz matches the design requirement, therefore the correctly tuned string meets the specification. In the second harmonic, there's a node at each end of the wave pattern and a node and an antinode and a node also at the center of the string. Two loops will therefore form, each loop with an antinode at its center. The string length is equal to exactly one full wavelength. Now, What you can do is adjusting the string length would alter the wavelength of the standing wave. Shortening the string increases the fundamental or first harmonic, raising the pitch. However, changing the length affects the physical feel and playing characteristics, so therefore musical design expects certain lengths, so adjusting the tension keeps these physical properties unchanged. Now additionally, adjusting string length risks upsetting harmonic tuning in resonance with other strings, so adjusting the tension rather than the length is a better, more musically consistent solution for correct tuning. In an experiment, microwaves are emitted into a rectangular metal cavity. One end of the cavity reflects microwaves completely, while the other end has a partially reflective mesh, allowing some microwaves to enter but also reflect back. The cavity is designed to create a stationary wave at its specific microwave frequency. Measurements show that the distance between two adjacent points of minimum microwave intensity inside the cavity is 1.5 centimeters. The experiment uses a microwave source operating at a frequency of 10 GHz. During a discussion, a student argues the stationary wave forms because two waves with different frequencies interfere. This spacing between adjacent minima represents a full wavelength of the microwave. Increasing the frequency would increase the distance between adjacent minima. Using the information provided, explain carefully why a stationary wave forms in the cavity and why the waves involved must have the same frequency. Analyze the distance between the adjacent minima observed in the cavity, deduce the wavelength of the microwaves, and explain your reasoning clearly. Assess Claim 2, made by the student, regarding the relationship between adjacent minima and the microwave wavelength. Evaluate Claim 3, made by the student. In your answer, consider the mathematical and physical relationships involved. So, pause the video now, then unpause the video when you want to go through your answer. Okay, in the first one, a stationary wave forms when two waves with the same frequency are travelling in opposite direction. Superposition occurs, producing constant regions of constructive and destructive interference. The reflection from the cavity surfaces ensures a coherent reflected wave. Now, different frequencies would lead to a non-constant phase difference, causing moving beats but not a stationary wave pattern. The next one, the distance between adjacent minima correspond to half a wavelength. So therefore the wavelength is going to be 2 times by 1.5 centimeters, which is 3 centimeters. So adjacent minima occur at wavelength over 2, lambda over 2 spacing in a stationary wave. Now claim 2 is incorrect. The distance between adjacent minima is half a wavelength, not a full wavelength. So in stationary waves, the nodes are separated by lambda over 2. Now claim 3 is also incorrect. From the wave speed equation v equals f lambda, increasing the frequency f would decrease the wavelength lambda. Therefore the spacing between minima would decrease, not increase. So the claim misunderstands the inverse relationship between frequency and wavelength when the wave speed is constant. A company designs outdoor wireless optical communication systems that use a laser beam to transmit data between two tall buildings across a city. To reduce noise and unwanted signals, polarizing filters are installed at both the transmitter and the receiver. The system transmits light polarized vertically. During a routine test, the transmission system shows a much better performance on dry, clear days than foggy or rainy days. Technicians note that rotating the receiving polarizer by 90 degrees with respect to the transmitting polarizer results in no signal being detected, even though the laser remains switched on. One engineer suggests adding a second polarizer at the receiver set at 45 degrees relative to the transmitter's polarization direction to recover part of the lost signal in case of misalignment. Explain using the properties of transverse waves why the laser light used for data transmission can be polarized. Describe why no signal is detected when the receiving polarizer is rotated by 90 degrees, referring to the behavior of polarized light passing through a polarizer. Explain how inserting a polarizer at 45 degrees between two cross polarizers allows some light to be transmitted. Without using detailed formulae, describe qualitatively how the intensity of transmitted light will compare to the original laser beam. Suggest and explain why the system performs worse in rainy or foggy conditions even though polarization is unaffected. So, pause the video now, then unpause the video when you want to go through your answer. Now, electromagnetic waves are transverse. The oscillations of electric and magnetic fields are perpendicular to the direction of energy transfer. A polarizer restricts oscillations to a single plane of vibration. Only transverse waves can be polarized, longitudinal waves cannot. Now, a polarizer transmits only a component of light oscillating parallel to its transmission axis. When the receiver polarizer is rotated by 90 degrees, its axis is perpendicular to the incoming light's polarization direction, so therefore no component of the electrical field passes through. Our transmitted intensity is zero. Now, light polarized vertically passes into a 45-degree polarizer. A 45-degree polarizer allows part of the vertically polarized light through, since the light has a component aligned with the transmission axis. After passing through the 45-degree polarizer, the light is now polarized at 45 degrees. When this light reaches the 90 degrees horizontal polarizer, it again has a component alignment with that axis, allowing partial transmission. Overall, the transmitted intensity is significantly reduced compared to the original beam, but not zero, so some signal is recovered. Now, lastly, rain and fog introduce the scattering of light. Scattering is caused by wave droplets or suspended particles. Scattering sends light energy in many directions, reducing the amount reaching the receiver. Now, scattered light is often depolarized, but the main issue is intensity loss, not polarization. So the rain and foggy conditions cause attenuation of the transmitted signal, leading to a poor performance. Two different experimental setups are investigated. Experiment 1, a string experiment. A string is fixed at both ends and vibrated at one of its resonant frequencies, producing a standard wave pattern. Nodes and antinodes are observed along the string. The second experiment is a water channel experiment. Surface water waves are generated at one end of a long open water channel, producing waves that travel along its length. The following observations are recorded. In experiment 1, certain points along the string remain completely stationary over time. In experiment 2, all points of the water surface oscillate, but none remain permanently stationary. In experiment 1, the distance between two adjacent nodes is 0.40 meters. In experiment 2, the distance between two adjacent wave crests is 1.6 meters. The time for a crest to pass a fixed point in the channel is measured at 2.0 seconds. Describe two different key differences between the motion of the particles in the stationary wave and the progressive wave based on observations. Using the data for experiment 1 and experiment 2, determine the wavelength of the standard wave on the string and the wavelength of the speed of the progressive wave on the water channel. Explain why the energy is transferred along the water channel in experiment 2 but not on the string in experiment 1. And a student suggests that if the string experiment was performed badly, the pattern would no longer be fully stationary. Discuss the validity of the suggestion and use the wave principles to support your argument. So, pause the video now, then unpause the video when you want to go through your answer. In the first one, in stationary waves, some particles at the nodes do not move at all, but in progressive waves, all particles oscillate with the same amplitude pattern moving through space. In stationary waves, no net energy is transferred along the medium, yet in progressive waves, energy is transferred in the direction of wave travel. The distance between adjacent nodes is half a wavelength, so the wavelength of the string is 2 times by 0.40 meters or 0.80 meters. The distance between adjacent crests is a wavelength, so the wavelength of the water is 1.6 meters. The period of the water wave is 2 seconds. Frequency is 1 over time period, so it's 0.5 hertz. The wave speed is the frequency times the wavelength, 0.80 meters. In a progressive wave, energy is transported along the wave as the particles successively oscillate. In stationary waves, energy is stored in the standard pattern of oscillations, oscillate between kinetic and potential energy without any net transfer, so therefore no energy will move from one end of the string to the other in experiment 1. Now, a good reflection is essential for forming a stable stationary wave and ensures identical waves travel in opposite directions. A poor reflection means the returning wave may have reduced amplitude or a different phase difference, preventing a perfect superposition. So the stationary wave pattern will become unstable or disappear, so the student is correct. A student connected a signal generator to a loudspeaker and placed the loudspeaker near one end of a long tube containing sand. The student adjusted the signal generator until the sand collected in small heaps as shown. Explain why the sand collects in small heaps. The student determined the distance d between the centers of adjacent heaps. Describe the procedure she should follow to determine an accurate value for d. Assess whether the experimental data is consistent with the value for the speed of sound of 340 meters per second. Signal generator frequency 3.25 kHz. D 5.1 centimeters. So, pause the video now, then unpause the video when you want to go through your answer. In the first one, a standard wave is set up with the interference of sound waves taking place in the tube. When constructive interference occurs, the amplitude is a maximum. When destructive interference occurs, the amplitude is a minimum. Our sand is displaced from the antinodes to the nodes. Now we should measure it over multiple heaps to get a multiple distances, divide by the number of gaps, not the number of heaps, and then repeat the measurement and calculate an average. We know that the wavelength is going to be 2 times the distance, so it's going to be 0.120 meters, centimeters into meters. V equals F lambda, so you get 332 meters per second, but it isn't the same as 340 meters per second. The photograph shows a stringed instrument called a cello being played with a bow. A standing wave forms on a cello string when the bow moves across the string. Deduce whether a thicker string will produce a note of higher or lower frequency compared with a thinner string. Assume each string is the same length and at the same tension. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know that a thicker string will have a greater mass per unit length. We know V is approximately going to be equal to the square root of T over mu. So with V being smaller, we know that V is equal to F lambda. The wavelength is constant, but now our frequency must therefore change, so the thicker string will give the lower speed, so you must have a lower frequency. The speed of a wave on a string can be described with the relation V equals the square root of T over mu, where T is the tension in the string and mu is the mass per unit length of the string. A string of length 0.69 meters has a mass of 9.0 times 10 to the minus 3 kilograms. A wave is travelling along the string with a speed of 203 meters per second. Calculate the tension in the string. When a string is fixed at both ends and plucked, a stationary wave is produced. Explain in terms of superposition of waves how the stationary wave is produced. The string is vibrating at its fundamental or first harmonic frequency of 270 Hz and produces the stationary wave pattern shown in 9a. 9b shows the same string vibrating at a frequency called its third harmonic. What is the frequency of the third harmonic? So, pause the video now, then unpause the video when you want to go through your answer. In the first one, mu equals mass over length, so you work it through to be 9 times 10 to the minus 3 over 0.69. V equals the square root of T over mu, so we can rearrange that, pop the values in, T equals 450 newtons. Now how does it work? Well, waves reflect from each end, they interfere because they're coherent, creating maxima and minima. The third harmonic is the third multiple of the first harmonic, so it's 3 times by 270, 810 Hz. So that brings an end to our revision session in today's lesson. So if we've been successful, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this lesson on progressive waves, which is a topic of waves in AQA A-Level Physics Paper 1. Thank you so much, and as always, have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics on the topic of waves in Paper 1, in particular looking at refraction, diffraction and interference. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you complete your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side. Then this left hand side section, write down your work and out and answers to the questions in the revision session. When you're doing this, make sure you write your answers in full sentences and show full working out. Whilst in the right hand side, write down any bits of information or any hints and tips on answering questions from this revision session, and after the end of the revision session write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics? Well, the first step is to look at the knowledge, learn the key facts, use your vision guides, class workbook, student prep notes and a textbook to learn the key ideas of the course. You may wish to make mind maps or write out notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca, the Student Knowledge Checker to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, practice exam style questions. Use exam prep books, homework books, supervised study books, additional workbooks to answer questions and mark your own work, and you may wish to download your own exam past papers to do this. So the 3 steps of learning the key facts, testing yourself and practicing exam style questions are how you should be revising for A-Level Physics. Now in this revision session we're going to be looking at 2 types of questions. Firstly, general check questions designed to probe your understanding of the key concepts of the topic. topic, and then assessment point questions, which are past paper examination questions which will mimic the types of questions found in public examinations. So let's start with these general check questions. The first question says, why does a wave diffract as it passes through a gap? So pause the video now, then unpause the video when you want to go through your answer. Well, a wave will diffract as it's compressed through a gap, which the wave that moves through the gap interferes and then produces a diffraction pattern. The next question says, why does little diffraction take place when the gap is much bigger than the wavelength of a wave? So pause the video now, then unpause the video when you want to go through your answer. Now, as the gap is large, the wave is not altered very much by passing through the gap, and therefore the interference process will not take place to produce the pattern needed. The next question says, why does little diffraction take place when the gap is much smaller than the wavelength of the wave? So pause the video now, then unpause the video when you want to go through your answer. Well, as the gap is very small, most of the wave will be absorbed by the wall, and then not enough of the wave will be present on the other side to form a strong diffraction pattern. The next question says, when is the most diffraction observed and why? So pause the video now, then unpause the video when you want to go through your answer. Well, most diffraction is observed when the wavelength is equivalent to the gap size it passes through. This is because when the slit width is comparable to the wavelength, all the diffracted waves will interfere constructively, resulting in a maximum of diffraction intensity. The next question says, when a wave encounters an object, why does a shadow form behind an object? Pause the video now, then unpause the video when you want to go through your answer. Well, a shadow forms as the object absorbs the wave, so there's no wave behind the object leading to the shadow. The next question says, when a wave encounters an object, why does a shadow not form behind the object over a large distance? So pause the video now, then unpause the video when you want to go through your answer. Well, as the wave diffracts, it hits the edge. The wave will diffract as it hits the edges of the object, causing the wave to spread out from this diffraction and fill in some of the shadow behind the object. The next question says, when a wave encounters an object, so why does the shadow form directly behind the object still? So pause the video now, then unpause the video when you want to go through your answer. Well, a shadow forms directly behind the object as the diffraction process has not yet occurred sufficiently at that point for the wave to be present behind the object. What property of a wave is altered during diffraction and why? Pause the video now, then unpause the video when you want to go through your answer. The only property of a wave that changes when it diffracts is its amplitude. That's because some of the energy is dissipated when a wave is diffracted through a gap. If in the same diffraction setup, blue light replaced red light, what would you observe in your diffraction pattern and why? So pause the video now, then unpause the video when you want to go through your answer. Well, the wavelength of red light is longer, so the light will diffract more, as the gap is now smaller than the wavelength, so the intensity fringes would therefore be wider. If, for the same light source, the slit was made narrower, what would you observe in your diffraction pattern and why? So pause the video now, then unpause the video when you want to go through your answer. If the slit was made narrower, the intensity would decrease as less of the wave is getting through, and the fringe spacing will be wider as more diffraction takes place. Why would this setup produce two coherent waves? So pause the video now, then unpause the video when you want to go through your answer. The wave will pass through the gaps, so it becomes two new wave sources. As both new waves originate from the same starting point, they'll have the same wavelength, they'll have the same frequency, so therefore they will be coherent. What will be produced on the far screen and why? So pause the video now, then unpause the video when you want to go through your answer. A pattern of maxima and minima would form as we get interference and superposition from the two waves produced from the gaps. When are bright fringes produced on the screen and why? Pause the video now, then unpause the video when you want to go through your answer. Bright fringes are produced when the path difference between the two sources is a multiple of a wavelength. This is because the waves will arrive in phase and constructively interfere. When are dark fringes produced on the screen and why? So pause the video now, then unpause the video when you want to go through your answer. Dark fringes are produced when the path difference between two sources is a multiple of half a wavelength. This is because the waves arrive out of phase and destructively interfere. What would happen to the fringe spacing if the distance from slit to screen is increased and why? So pause the video now, then unpause the video when you want to go through your answer. When the distance from slit to screen increases, the fringe spacing increases. This is because the greater the distance from slit to screen, the greater the wave can spread out due to diffraction, so the fringe spacing is larger. What would happen to the fringe spacing if the slit spacing increased and why? So pause the video now, then unpause the video when you want to go through your answer. When the distance from the slit spacing increases, the fringe spacing decreases, because when the slits are closer together, the path difference is smaller, so the light waves must travel less distance to interfere constructively or destructively. What would happen to the fringe spacing if the wavelength of the source increased and why? So pause the video now, then unpause the video when you want to go through your answer. When the wavelength of the source increases, the fringe spacing increases, because as the wavelengths are now larger, the path differences are now larger values, so the fringe spaces must increase accordingly. Why is it difficult to measure the distance between adjacent fringes in the Young's double slit experiment? So pause the video now, then unpause the video when you want to go through your answer. The distance from the centre of one fringe to the centre of the adjacent fringe will be a very small value, so this will give a large percentage uncertainty when this value is measured with a ruler. How can the accuracy of the fringe spacings be increased in the Young's double slit experiment? So pause the video now, then unpause the video when you want to go through your answer. Well, measure the distance between several fringes and divide by the number of measurements taken. This gives an average value and reduces random error. Now remember, when you're taking your values though, it's the number of spacings, not the number of fringes, that you will divide by. Why does diffraction take place when a wave passes through a diffraction grating? So pause the video now, then unpause the video when you want to go through your answer. A diffraction grating has many gaps in it, so the wave will diffract through each gap to produce a diffraction pattern. Why is the diffraction pattern from a diffraction grating bigger than the diffraction pattern from a Young's double slit? So pause the video now, then unpause the video when you want to go through your answer. Well, a diffraction grating has many gaps in it, whilst a Young's double slit has 2 gaps in it. This therefore means more light will pass through the diffraction grating. The next question says, why is the diffraction pattern from a diffraction grating sharper than the diffraction pattern from a Young double slit? So, pause the video now, then unpause the video when you want to go through your answer. In a diffraction grating, the space between the slits is much smaller, so the fringe spacing is smaller and sharper as there's more instances of interference taking place. Which apparatus results in more accurate values being taken for fringe spacing, the Young double slit or the diffraction grating, and why? So, pause the video now, then unpause the video when you want to go through your answer. Well, the diffraction grating, as the fringes are sharper, so it's easier to measure the gaps between them with a greater accuracy. What is the path difference between the waves at the central beam of an interference pattern? Pause the video now, then unpause the video when you want to go through your answer. The path difference is 0, as is the 0th order of the interference pattern. What would happen to the angle to the normal if the distance between the slits increased and why? So pause the video now, then unpause the video when you want to go through your answer. If the distance between the slits increased, the diffraction effect is lessened, so the waves don't spread out as much before interfering, so therefore this will cause the angle to decrease. What would happen to the angle if the wavelength of the wave increased and why? So pause the video now, then unpause the video when you want to go through your answer. If the wavelength increased, the diffraction effect is increased as the wavelength is even greater than the slit space, so the waves do spread out more and this causes our angle to increase. Can an infinite number of orders of maximum be produced by a diffraction grating and why? So pause the video now, then unpause the video when you want to go through your answer. No, only a finite number of orders can be produced, as there's a maximum angle of diffraction, 90 degrees, as the diffraction grating is at right angles to the incident beam. If the diffraction grating experiment can produce beams up to the third order, how many beams will be on the screen? Pause the video now, then unpause the video when you want to go through your answer. There will be a maximum of 7 beams on the screen. There'll be 3 beams on each side of a central maxima and the central maxima itself. If a diffraction grating experiment can produce beams up to the 7th order, how many beams will be on the screen? So pause the video now, then unpause the video when you want to go through your answer. Well, there will be 15 beams on the screen. There will be 7 beams each side of the central maxima and the central maxima itself. What happens to the speed of the wave if it moves into a denser medium in y? So pause the video now, then unpause the video when you want to go through your answer. The speed of the wave slows down in a denser medium. An electromagnetic wave always travels at the speed of light, but in a material it travels at the speed of the light until it hits an atom. It's then absorbed and re-emitted, which takes a small amount of time. The more this happens, the slower the effective average speed. So the more dense the material, the more atoms that are in the way to do this. The next question says, what happens to the frequency of a wave if it moves into a denser medium in y? So pause the video now, then unpause the video when you want to go through your answer. The frequency of a wave is a fixed value. The frequency will be an unchanging value as it's due to the photons that make the electromagnetic wave, and thus it can't be varied. Why does a wave bend when it moves into a medium of a different refractive index? So pause the video now, then unpause the video when you want to go through your answer. The refraction effect is observed as the wave hits the new material at an angle, so not all of the wavefront will change speed at the same time. This difference in the change of speed for the wavefront will cause a variation in speed across the wavefront, which produces the bending effect of refraction. Under what 2 circumstances would refraction not be observed in a wave when it moves between 2 media and y? So pause the video now, then unpause the video when you want to go through your answer. Refraction is not observed if the wave hits the new medium along the normal, as the wavefront will change speed at the same time, or if the 2 media had the same refractive index, as the wave would not change speed at any point. What is the change in direction in the path of a wave when it moves into a denser medium in y? So pause the video now, then unpause the video when you want to go through your answer. When it moves into a denser medium, the wave will bend towards the normal, as the light travels between 2 points along the path that requires the least time as compared to the other nearby paths. Light travels more slowly in a denser medium, and hence will therefore bend towards the normal. What path will be taken by the path of a light ray as it hits a triangular glass prism coming from air and y? So pause the video now, then unpause the video when you want to go through your answer. It would appear that the light would be travelling parallel through the prism. The light ray would refract towards the normal when it enters the glass prism, and then away from the normal as it leaves the prism, giving an impression of a parallel line. What would happen if white light moved between 2 different media and y? So pause the video now, then unpause the video when you want to go through your answer. The white light would break up into different parts of the spectrum, as the different colours of the light would each travel at different speeds in the new medium. Which colour of light would have a larger angle of refraction if white light was shone through the 2 media, blue or red, and why? So pause the video now, then unpause the video when you want to go through your answers. Blue light would have the larger angle of refraction, as it has the shorter wavelength of wave, given the greater refraction. Which colour of light would spread out more if white light was shone between 2 media, blue or red, and why? So pause the video now, then unpause the video when you want to go through your answer. Blue light would spread out more on the new medium, as it has a shorter wavelength of wave, giving a greater refraction. So, why is the sky blue on Earth? Pause the video now, then unpause the video when you want to go through your answer. Well, white light enters the atmosphere after being emitted from the sun and travelling through space. Upon entering the atmosphere, blue light refracts more as it has a lower wavelength, so will spread out more, giving the sky its blue colour. Why is the sky red on Earth at sunset? So pause the video now, then unpause the video when you want to go through your answer. The light has had farther to travel to get to the ground at sunset. This means that the refraction and scattering of the blue light will have happened at a point further away from the surface of the Earth. This leaves only the red light to refract at this point, giving the sky a reddish colour. What is total internal reflection? Pause the video now, then unpause the video when you want to go through your answer. Total internal reflection is the complete reflection of light that occurs when a light ray travelling in a medium with a high refractive index encounters a boundary with a medium of a lower refractive index at an angle greater than the critical angle. Why does total internal reflection occur? Pause the video now, then unpause the video when you want to go through your answer. Total internal reflection occurs when the angle of incidence exceeds the critical angle. At this point, the refracted ray would have an angle of incidence in the second medium that is greater than 90 degrees, making it impossible for the light to continue into the second medium. Instead, the light is completely reflected into the first medium. When does total internal reflection occur and why? So pause the video now and unpause the video when you want to go through your answer. Total internal reflection occurs when a light ray moves between media of different refractive indices, because the effect of total internal reflection is caused by the refraction. For total internal reflection to occur, why must the refractive index of the second medium be less than the first one? So pause the video now, then unpause the video when you want to go through your answer. Total internal reflection occurs when a light ray moves into a lower refractive index. That's because as it moves to a less optically dense medium, the ray travels faster. This means it's travelling so fast that refraction is so extreme, it in fact becomes reflection. What is so special about the critical angle? Pause the video now, then unpause the video when you want to go through your answer. The critical angle is the exact point between two media where the light transitions from carrying out refraction into carrying out reflection. At this angle, the light ray will refract so much that it will start to reflect back into the medium. It's refracted so much it's bent back onto itself. How can the critical angle be identified? Pause the video now, then unpause the video when you want to go through your answer. The critical angle is when the reflected/refracted ray is moving parallel to the boundary between the two media. If the angle of incidence is below the critical angle, what will happen and why? So pause the video now, then unpause the video when you want to go through your answer. Below the critical angle, the light ray will refract into the new medium. This is because the refraction that's carried out at the boundary is small enough to allow refraction by transmission through the material. What types of wave carry out total internal reflection? So pause the video now, then unpause the video when you want to go through your answer. All types of waves will carry out total internal reflection as refraction is a property of all waves. What is the benefit of having a low critical angle when using total internal reflection to transmit data? So pause the video now, then unpause the video when you want to go through your answer. A low critical angle will mean that there are many angles at which total internal reflection will occur. This will allow a lot of data to be transmitted. What is the drawback of having a low critical angle when using total internal reflection to transmit data? So pause the video now, then unpause the video when you want to go through your answer. A low critical angle will mean that there are many angles at which total internal reflection will occur, so there are many varied paths for the data to take, so the data would spread out and arrive at the destination at different times. Fibre optics can be referred to as a single mode. What does this mean and why are they designed this way? So pause the video now, then unpause the video when you want to go through your answer. Single mode means that there's only one path that the light can travel in the fibre optic. This is achieved by having a very narrow core. This prevents the light ray spreading out over its journey or modal dispersion and would cause pulse broadening. Why can white light not be used in fibre optics for data transfer? So pause the video now, then unpause the video when you want to go through your answer. As the white light would travel down the fibre optic, the different colours of light would travel down at different angles, so the distance travelled would be different. This would cause the different colours of light to spread out, which is called material dispersion and causes pulse broadening. What colour light would travel in a fibre optic the fastest and why? So pause the video now, then unpause the video when you want to go through your answer. Red light will travel faster as this refracts the least when it hits a new medium. This means the path it takes will be straighter than the blue light, so it will travel in a faster time as they're both travelling at the same speed. Why must the fibre optic be made of a transparent medium? Pause the video now, then unpause the video when you want to go through your answer. Well, the fibre optic transmits information via total internal reflection. If the medium of the core was not transparent, then the information will be absorbed as it moves through the fibre optic. Why must the cladding of the fibre optic have a lower refractive index than the core? So pause the video now, then unpause the video when you want to go through your answer. Total internal reflection occurs when a light ray moves into a lower refractive index, the cladding. This is because as it's moving to a less optically dense medium, the ray travels faster. This means it's travelling so fast that the refraction is so extreme it becomes reflection. What is the benefit of having a fibre optic with a low critical angle? So, as mentioned before, a low critical angle means that there are many angles at which the total internal reflection will occur. This allows a lot of data to be transmitted. What is the advantage of using fibre optics to transfer data as opposed to copper wires? So, pause the video now, then unpause the video when you want to go through your answer. Well, the advantages of the fibre optics are that they're more secure, they have a higher bandwidth, a lower attenuation, they're much lighter, there's no crosstalk or interference, it's safer near high voltage equipment, it has longer transmissions without repeaters, and it uses more communication channels. What is the disadvantage of using fibre optics to transfer data as opposed to copper wires? Pause the video now, then unpause the video when you want to go through your answer. The disadvantage of the fibre optics are that the new infrastructure will be required, it's more difficult to mend or join together, and it can't carry electrical power that much. It will also break if bent too much. For a fibre optic, what is a digital signal? So pause the video now, then unpause the video when you want to go through your answer. In a fibre optic, the information is transferred via a light ray. So a digital signal is binary, so it consists of the light ray being on or being off. Why are digital signals used in fibre optics? Pause the video now, then unpause the video when you want to go through your answer. A digital signal is used is either 0 or 1 because even if the signal is distorted, the original signal can be restored at the end to be back to either 0 or 1. Now let's have a look at some exam style questions to do with waves. An engineering team designs a high-speed digital communication link between two islands using optical fibre laid beneath the sea. The fibre is constructed from a chlor and a cadmium, both made of silica-based glass with the following properties. A short pulse of infrared light is launched into the fibre. Initial measurements show the pulse duration to be 2 nanoseconds. After travelling a distance of 50 kilometers through the fibre, the pulse duration broadens to 5.5 nanoseconds due to dispersion and absorption effects. A researcher makes the claim that simply reducing the core diameter will eliminate pulse broadening entirely, ensuring a perfect signal integrity. Use the principle of Snell's law and total internal reflection, explain clearly why the optical fibre must have a cladding with a lower refractive index than the core. Calculate the critical angle at the boundary between the fibre core and the cladding and explain why this calculation is significant for signal transmission. From the data provided, calculate the percentage increase in pulse duration after travelling 50 kilometers through the fibre, and then critically evaluate the researcher's claim that reducing the core diameter will entirely eliminate pulse broadening. Your evaluation should discuss the roles of material dispersion, modal dispersion, and absorption. So pause the video now and unpause the video when you want to go through your answer. Okay, in this first one, the cladding refractive index must be lower to achieve total internal reflection at the boundary. Using Snell's law at the boundary, with end core being greater than end cladding, the refraction bends away from the normal. So this ensures that the angle of incidence within the fibre is greater than the critical angle, trapping the light within the core. Without this lower index cladding, the light would refract out, causing a signal loss. Now we know sine critical angle is equal to the end cladding over the end core. So you work it through to be 78.5 degrees. Now the critical angle is significant as is the minimum angle for total internal reflection. So light must strike the boundaries at angles greater than 78.5 degrees to remain trapped, ensuring efficient transmission. Now the percentage decrease is going to be 5.5 minus 2 over 2 times by 100, which is 175%. Next, we know reducing the core diameter helps decrease modal dispersion by restricting the number of possible paths. However, material dispersion still remains due to the properties of the glass. Absorption is also unaffected by changing core diameter, so still broadens the pulse by weakening the intensity. Thus, even if the modal dispersion is reduced significantly, material dispersion and absorption still limit how sharp the pulse is. So the researcher's claim is incorrect. Reducing the diameter does help reduce pulse broadening, but can't eliminate it entirely. You need to combine the optimization of multiple factors to get the best performance. On a hot day, an observer notices distant objects such as trees appear to have reflections beneath them, despite the absence of water. This optical phenomenon is known as an inferior mirage. A physics student investigates this by measuring how the refractive index of air near the ground changes with temperature. They collect the following data at various heights above a hot asphalt road. The refractive index of the cooler upper air is approximately 1.000293. The student hypothesizes that the total internal reflection within the layers of air is responsible for the mirage. Explain clearly why variations in air temperatures above a hot surface changes the refractive index. Calculate the critical angle at the boundary between the air layers 0 cm and 100 cm above the ground. Explain clearly what this calculation implies physically about light rays travelling through these layers. And then finally, evaluate critically the student's hypothesis that the total internal reflection within the layers of air is the cause of the inferior mirage. Consider the strengths and limitations of this hypothesis in the context of your data analysis. So, pause the video now, then unpause the video when you want to go through your answer. Okay, hot air is less dense due to the expansion, and cooler air is therefore denser. The refractive index depends on the density. The less dense air has a lower refractive index, and the denser air has a higher refractive index. Therefore, the temperature gradients near the surfaces produce refractive index gradients as well. Now, we know that sine critical angle is n upper divided by n lower, so you work it through, and the critical angle will therefore be equal to 1.00029 before we take the sine of that. This is slightly greater than 1, so it physically implies that the layers are extremely close in the refractive indices, so the true critical angle calculation isn't achievable directly between these two layers, since the total internal reflection strictly requires a lower refractive index. So the gradual refractive index gradient rather than a sharp boundary is needed, so thus the continuous bending rather than one single reflection occurs in these mirages. Now, the refractive index gradient is clearly supported by the data and explains why the light is bending towards the regions of a high refractive index. The observed trend indicates conditions for refraction are plausible near the ground surfaces. Now, the total internal reflection strictly requires discrete boundary layers with a significant index difference and defined interface, which is not shown in the data. Now, real mirages typically involve a continuous gradient refraction rather than a discrete boundary reflection, which better describes the observed mirages. So the hypothesis has got merit, but it oversimplifies the scenario. A more refined hypothesis involving a continuous gradient refraction rather than a strict total internal reflection will be a more accurate idea of the situation. The next question says, a diving company investigates how vision underwater is affected by refraction. When divers use standard air-filled masks, they can clearly see underwater. Before attempting to see without masks, vision is then severely distorted. The company's technicians record the refractive indices of relevant materials. A diver without a mask tries to view an object underwater. The technician suggests the diver's inability to focus is due to refraction occurring directly at the water-eye boundary. Explain using refractive indices and Snell's law why vision is significantly impaired underwater without a diving mask. Calculate the critical angle for the boundary between the diver's eye lens and fresh water. Clearly interpret the physical meaning of your result. A researcher proposes that the divers would see better if the masks were filled with water instead of air, as would remove a refractive boundary. Evaluate this claim critically using the relevant data provided. And then another technician suggests increasing the refractive index of the mask glass substantially to around 2.4 to further improve underwater vision. Critically discuss this practically and potential consequences of this suggestion. So pause the video now, then unpause the video when you want to go through your answer. Okay, in this first one, without a mask, refraction occurs directly at the water-eye boundary. The refractive indices of the eye lens and the water are very close, reducing refraction at this boundary significantly. Now, most refraction normally happens at the air lens boundary, so underwater this boundary is effectively removed, resulting in a minimal focus and power. Therefore, the eye cannot focus correctly underwater, so it causes significant blurring. We know that the sine critical angle is n water over n lens, so the angle is going to be 70.2 degrees. Beyond this angle, total internal reflection occurs within the eye lens. So rays entering the eye at very shallow angles may not enter effectively, contributing to further impaired vision. Filling the mask with water would indeed remove the air to glass and air to lens boundaries, reducing refractive discontinuities. However, this would replicate conditions similar to the no mask, given a minimal refractive focusing at the surface. So the eye lens alone is insufficient for underwater focusing due to similar refractive indices. The visions would remain blurred, so the researcher's claim is incorrect. Filling the mask with water does not improve vision and essentially removes the benefits provided by the air to glass and the air to eye interface. Finally, high index glasses are costly, heavier and more fragile, making them less suitable practically. Higher refractive index could indeed increase refraction, enhancing the initial focus and power, and the high index glass will cause significant optical distortions like chromatic aberration and dispersion, which would potentially outweigh any focus and benefits and worsen the overall clarity. A research team is designing a compact spectrometer to analyse light from distant stars. They perform preliminary experiments using two setups. Experiment 1, a monochromatic laser with a wavelength of 650 nanometers is passed through a single narrow slit of width 1.5 times 10 to the minus 4 meters. They record a diffraction pattern produced on the distant screen. A white light source is passed through the same slit in experiment 2 and diffraction effects are observed. Separately, the team tests the diffraction gradient with 500 lines per millimeter at normal incidence to study stellar spectra. They observed that for certain bright spectral lines, the diffraction maxima occurred the following separations. Describe qualitatively how the diffraction pattern observed in experiment 1 would differ from that observed in experiment 2. Explain how changing the slit width would affect the width of the central diffraction maximum in both experiments. Use the information provided for experiment 1 to determine the angular width between the first minima of the central diffraction maximum. Then analyse the diffraction gradient data. Estimate the wavelength of the light corresponding to the bright spectral line observed. Explain your method clearly. Comment on how the use of diffraction gradients help in the study of stellar spectra. So pause the video now, then unpause the video when you want to go through your answer. In this first one, monochromatic light produces a central bright fringe with symmetrical side fringes of decreasing intensity. White light produces a central white fringe, but coloured fringes appear at the wider angles. The different wavelengths diffract by different amounts, so the red spreads more than blue. The white light pattern will appear broader and more complex due to this wavelength-dependent diffraction. Secondly, narrowing the slit widens the central diffraction maximum, widening the slit narrows the central maximum. In both monochromatic and white light cases, the effect is consistent. Slit width inversely affects the spread. So for white light, the broader slit would compress all colour fringes, narrower slits exaggerating the colour separation. We know d sine theta equals n lambda, so you can work this through and you get theta to be 0.248 degrees. Therefore the full angular width is that times by 2 because it's either side of the central maxima, so it's 0.496 degrees. Finally, d sine theta equals n lambda. We know d is 1 over 500 times 10 to the 3, so therefore it's 2 times 10 to the minus 6. So therefore we work out lambda, we put all the values in, to be equal to 584 nanometers. This is a wavelength in the visible range. It's a yellowy-orange visible light. So the diffraction gradients will allow precise wavelength measurements by separating the light into distinct maxima. Essential for stellar spectroscopy, it will identify elements and determine redshifts. In a lab experiment, a laser of wavelength 640 nanometers is directed at a double slit arrangement. The slit separation is measured at 0.35 millimeters and the screen is placed 2.5 meters away to observe the resultant interference pattern. Later, the same apparatus is used with a white light source after adjusting the experimental setup to ensure a coherence between the slits. Observations and key measurements are recorded. The team also discussed how early experiments like Young's helped challenge the particle model of light, influence the development of the modern theories of electromagnetic radiation, explain why using a laser improves the clarity of the interference fringes compared to using an ordinary light bulb. In your answer, refer to coherence and path difference. Calculate the fringe spacing observed with the laser in the initial setup. Explain qualitatively why the interference pattern changes when the white light is used instead of the monochromatic light. The lab technician suggests that using a laser carries no safety risks because the power output is low. Critically evaluate this claim. Then discuss how the Young's double-slit experiment helped advance the understanding of the nature of electromagnetic radiation and why it posed a problem for the particle model of light at the time. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, lasers produce coherent light, so they've got a constant phase difference and the waves have the same frequency. Ordinary sources like bulbs are incoherent. They have a random phase relationship, so there's no interference pattern. So the path difference between the laser waves at the double slits leads to a stable and constructive and destructive interference. Therefore, the laser creates sharper, stable, bright and dark fringes. We know that W equals lambda d over s. Pop in all the values, you get 4.57 times 10 to the minus 3 meters. White light contains ranges of different wavelengths. Different wavelengths will interfere differently, with their fringe spacings dependent on the wavelength. The central fringe remains white because all the colours superpose, whilst the outer fringes show a colour separation. Red fringes further away than blue. Now, even low-power lasers can cause eye damage due to the concentrated energy in focusing by the lens on the retina. Now, safety risks include temporary or permanent vision damage if the laser beam is directly observed, so therefore appropriate precautions are essential despite the low power. Now, Young's experiment demonstrated light interference, implying wave behaviour. This challenged the Newton particle theory of light, which couldn't explain stable interference patterns. So this supported development of wave models and ultimately influenced the understanding of electromagnetic waves as oscillating electrical and magnetic fields. A laser of wavelength 580 nanometers is used in a Young's double-slit experiment. The slits are separated by 0.30 millimeters and the screen is positioned 2.0 meters away. The experiment is repeated with a different laser of unknown wavelengths, resulting in a measured fringe spacing 20% smaller than that of the original setup. The experimenters also observed the effects of slightly misaligning the slits and briefly exposing the laser beam to open air without beam controls. Describe the conditions needed for a stable interference pattern to form the Young's double-slit experiment and why coherence is important. Calculate the fringe spacing produced by the original 580 nanometer laser. Determine the wavelength of the second laser that produces the fringe spacing that is 20% smaller. Explain with a reference to the path difference why bright and dark fringes form on the screen. A student suggests that misaligning the slits slightly horizontally would have no significant effect on the interference pattern. Assess this suggestion. Then the experimenter briefly removes beam limiters and warning signs from the laser setup during testing. Discuss the risks associated with this action and explain why specific laser safety protocols must always be followed, even with low-powered lasers. So pause the video now, then unpause the video when you want to go through your answer. Right, the two sources must be coherent, have a constant phase difference and frequency and wavelength must be the same. The light from the slits must have a similar amplitude for clear fringes. Coherence ensures that constructive and destructive interference is stable over time. Without the coherence, the phase difference is random, which would cause the pattern to blur and disappear. W equals lambda d over s, pop in all the numbers, we get 3.87 times 10 to the minus 3 meters. We work out our new fringe spacing, which is 80% of the old one, so it's 3.096 millimeters. Pop in the values, we get 464 nanometers. Next one, bright fringes occur where the path difference between the two waves is a whole number of wavelengths. It's constructive interference. Dark fringes occur when the path difference is an odd multiple of half wavelengths. It's destructive interference. The path difference alters the phase relationship between the waves, leading to regions of maximum and minimum on the screen. Now, the slightly horizontal misalignment can cause the wavefronts to arrive at slits with slightly different phases. This reduces the fringe contrasts, so therefore the student's suggestion is incorrect. The misalignment would affect the visibility and the sharpness of the fringes even if the slit separation remains constant. Now, without beam limiters and warning signs, there's a risk of direct or reflected exposure to the eyes, leading to permanent damage to the retina. Laser safety protocols are essential even with low-powered lasers to prevent accidental injury. Now, a laboratory is analysing light emitted by an unknown distant star to determine its elemental composition. A diffraction gradient of 600 lines per millimeter is used in the spectrometer setup. The observed spectral data are as follows. The team notes that the second order, n equals 2, the violet line is at the limit of the detection system. Explain qualitatively why a higher order maxima appear fainter even for the same spectral line. Use the data to determine the wavelength of the violet and red lines. Show your full reasoning. Based on the calculated wavelengths, identify the likely elements responsible for the two spectral lines using the following rough emission data for elements. Then evaluate how confident you can be in this elemental identification based on the diffraction gradient method alone. In your answer, consider the strengths, limitations, and any assumptions that could undermine your conclusion. So, pause the video now. Then unpause the video when you want to go through your answer. Right, in this first one, high order diffraction spreads energy over wider angles, so the diffraction efficiency often drops sharply for the higher orders, so therefore higher orders appear fainter for even strong spectral lines. Next one, we say d sine theta equals n lambda. D is 1 over 600 times 10 to the 3. So for the violet line, we can work it through, lambda pop it in there, pop the values in, we get 612 nanometers. For the red line, we do the same. We get 853 nanometers. 853 nanometers is outside the visible red spectrum, so you will need to not use that order, but the second order instead. And also, multiple lines may overlap at different orders, making it harder to make a judgment. 612 nanometers is close to the red oxygen line, but it's not perfect, but it could be plausible. That's that one. 853 nanometers is too high, so it's either misidentified or it's infrared. It's not one of the three lines given, so only oxygen identification has weak support, so we need some better data to confirm. Finally, diffraction gradients offer a higher angular resolution, leading to more accurate wavelength measurements. We can separate closely spaced spectral lines, which is ideal for stellar analysis. The overlap between the different orders could cause line misidentification if not accounted for. We may get observational errors which affect the wavelength calculation heavily. Only a few strong lines will be observed, and you could miss the weaker lines necessary for accurate identification. We assume normal incidence and perfect gradient calibration. Real setups often aren't perfectly calibrated. There's a reasonable first identification but needs cross-checking with other independent measurements, so you have a bit of confidence, but it's not enough for a definite elemental assignment. Following the early experiments, the research team wants to study very fine structures and interference patterns. They set up a double slit experiment using a narrow single slit with width 0.080 millimeters, placed in front of the double slits to limit the wavefront width. The set of parameters are shown as following. They observe a broad diffraction envelope within the double slit fringes which are modulated. Some fringes become very faint or invisible near the edges of the diffraction pattern. Explain why introducing a single slit in front of the double slits causes the double slit fringes to be modulated by a broader diffraction envelope. Calculate the angular width of the broad diffraction pattern caused by the single slit. Estimate the number of bright fringes visible within the central maxima produced by the single slit, and suggest one experimental adjustment that would allow for more double slit fringes to be observed clearly within the diffraction envelope. Explain your reasoning. So, pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, a single slit acts as a diffraction source, producing a broad diffraction pattern. The light reaching the double slits is now diffraction limited, affecting the overall intensity distribution. The double slit interference fringes are modulated in intensity by the single slit diffraction envelope. It's bright in the centre and it fades towards the edges. We know d sine theta equals n lambda, so we can pop it all through. We get theta to equal 0.415. The angular width is between the two max minima on either side of the central maxima, so you double it, it's 0.83 degrees. Now we know change in theta equals lambda over s, so you can pop in the values and we get it to be 1.93 times 10 to the minus 3 radians, which is 0.11 degrees. Now the number of bright fringes in the central maxima is 0.83, which is the overall angle we just calculated, divided by 0.11, so it's 7.5, so rounds down to 7. Now, what we could do is decrease the slit width. A single slit is wider and a narrow diffraction pattern, or you could increase the double slit separation. This would either of them would narrow the diffraction envelope or increase the number of fringes fitting in it, improving the visibility across the pattern. A ray of monochromatic light is incident on a glass prism as shown. Show that the refractive index of the glass for this ray of light is 1.89. State what is meant by the term the critical angle and calculate the critical angle for this light in the prism. Complete the diagram below to show the path of the ray as it passes through the prism and emerges into the air. So pause the video now, then unpause the video when you want to go through your answer. In this first one, we say n is equal to sine theta 1 over sine theta 2, pop in the values, n equals 1.89. The critical angle is the angle of incidence such that the angle of refraction becomes 90 degrees. We know that the sine critical angle is 1 over n, or 1 over 1.89, so theta equals 31.9. So what we can do is, we can see in the diagram, we can draw in the values, we look at the laws of angles and we work out our values to get the following diagram as shown. Note we get total internal reflection for 1 mark. We can see that the angle it hits the second side at is 38 degrees. You'll get refraction away from the normal because we're now going into a less dense medium, and then it's going to be between 22 and 45 degrees. A student is carrying out an experiment to investigate the interference of sound waves. Two identical loudspeakers L1 and L2 are connected to a signal generator as shown. A sound level meter is moved from A to B and a series of maxima are detected. The sound waves emitted from the loudspeakers are coherent. State what is meant by coherent. Explain in terms of waves how a maxima is produced. Then the wavelength of the sound wave is 0.400 meters. The distance from L2 to the third order maximum at point P is 6 meters. Determine the distance from L1 to P. Then a second student in the room is wearing a pair of active noise cancelling headphones. The student switches on the ANC function. The sound level from the loudspeakers heard by the student decreases significantly. Name the type of interference that the headphones use to reduce the sound level. So pause the video now and then unpause the video when you want to go through your answer. Right, in this first one, the sound waves from the loudspeaker have a constant phase relationship, have the same frequency, same wavelength, same velocity. The maxima is produced when the waves meet in phase. We know the path difference because the meeting in phase is n lambda, so it's another third order, so it's 3 times by 0.4. That equals the path difference, so 3 times by 0.4 equals 6 minus the other path, so therefore the other path is 4.8. This must lead to destructive interference. Lighthouses are located along coastlines to aid navigation. A lighthouse emits an intense beam of light. In clear weather, the beam is visible for long distances, but in foggy weather, the visibility of the beam is limited. The beam is refracted by water droplets in the air. A light ray in the beam is incident on the spherical water droplet with an angle of incidence of 40 degrees. The ray passes through the droplet and meets the water-air boundary at x as shown. Deduce whether the ray leaves the water droplet at a point x. The speed of light in the water is 2.25 times 10 to the 8 meters per second. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we know that n for air to water is 3 times 10 to the 8 over 2.25 times 10 to the 8 is 1.33. So therefore we can say n sine theta 1 equals n sine theta 2. So we can say 1 times by sine 40 equals 1.33 times by sine theta 2. Theta 2 equals 29. So therefore we know that the critical angle, sine critical angle is 1 over 1.33. So we know it's 49 degrees. That is greater than 29. So you get refraction. Calculate the largest angle theta to the axis at which the light can travel for long distances through the core of a multimode fibre if the refractive index of the core is 1.574 and the cladding is 1.550. Explain what would happen to the light entering the fibre at an angle to the axis greater than the angle calculated in 1.1. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that 1.57 sine critical angle is equal to 1.500 times by 1. So therefore C, is going to be 80 degrees. So therefore the angle, which is the opposite side to the critical angle, which must overall equal to 90, is therefore equal to 10 degrees. So therefore, if it was at a greater angle, then refraction would take place and the total internal reflection wouldn't happen. Now this means that some reflection or intensity would rapidly fall and the light would escape from the glass and the light will go into the cladding, so it won't transfer the energy efficiently. So that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this revision session on waves, which is part of the paper 1 for AQA A-Level Physics, in particular looking at refraction, diffraction and interference. Thank you so much and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 1 on the topic of waves. So in today's revision session we're going to look at how to answer examination questions for A-Level Physics Paper 1, in particular the waves topic. So if we're being successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics of the waves module we need to improve upon for AQA A-Level Physics. So how should we be carrying out this particular revision session? When completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section, write down your working out and answers to the questions which you cover in the revision session. When you're doing this, make sure you write in full sentences and you show your full working out for calculations. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising your A-Level Physics exam for your A-Level Physics examination? Well, the first thing you should be doing is learning the key facts. So use things like revision guides, class workbooks, prep notes, and textbooks to learn the key ideas of the course. So you may wish to make mind maps or write out notes yourself. The second step is to retrieve your knowledge and understanding. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then step 3 is to practice examination style questions. So use the examination prep books, homework books, supervised study books, additional workbooks to help answer examination questions and mark your own work. Now you may wish to download your own examination papers to do this. So those 3 steps are learning the key facts, then testing yourself, and then practicing examination style questions. Now, as we're carrying out revision in this particular session, you'll find that we'll cover 3 types of questions. The first type of question is a general check question. So these are basic questions designed to probe your understanding of the key concepts of this particular topic. The second type of question we're going to look at are checkpoint questions, which are the more challenging questions designed to place your knowledge and understanding of the topics into different contexts and different applications. And then finally, we've got assessment point questions, which are past paper examination questions, which will mimic the type of questions found in public examinations. So let's have a look at this topic of waves. So in this first question, which will start with the general check questions, is looking at the following. So figure 2 below shows the displacement of a string as the wave travels along the string. Now firstly, from looking at figure 2, give the amplitude of the wave, then secondly, give the wavelength of the wave, and then thirdly, a different transverse wave has a wavelength of 1.8 meters and a frequency of 16 Hz. From this information, calculate the speed of this wave. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the amplitude of the wave is from the equilibrium position or the midpoint to either the top or the bottom of the wave. So you can see here it's 19 centimeters from the central point to the maximum displacement, either positively or negatively, so you get your 19 centimeters. Now your wavelength is going to be 80 centimeters because it is after 2 of your amplitudes, or you could also argue it's when the wave starts to repeat itself again, so it's at 80 centimeters. And then finally, speed is equal to frequency times by wavelength, so we do 16 Hz times by 1.8 meters, and we get our answer to be 29.0 meters per second. Now our next question shows figure 1, which has a displacement of a surface water wave with time. Firstly, identify the number of oscillations shown in figure 1, then give the amplitude of the surface water wave shown in figure 1, and then give the period of the surface water wave shown in figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work out how many oscillations there are? Well, you can see that there are 2.5 oscillations, because each oscillation, each entire wave, is actually when the wave goes back to the start again, after it's gone positive, then negative, and then back to the start again. That's one oscillation, or one wave. So you'll notice it goes backwards and forwards until 20, then backwards and forwards again at 40, and then forwards again, so you get 2.5 waves. Now, what's the amplitude? Again, the amplitude is from the midpoint up until the maximum displacement, either positively or negatively, so that is 8 centimeters. And then the time period, you know that time period is actually, again, the time it takes for it to have one complete oscillation, so it's 20, because that's the point at which the wave starts to repeat itself. The next question says, calculate the phase difference in degrees between 2 points on a wave of wavelength 40 centimeters separated by, firstly, 20 centimeters, then 40 centimeters, then 80 centimeters. Then calculate the distance between 2 points on a wave of wavelength 1.60 meters when they've got a phase difference of 90 degrees, 540 degrees, and 5 pi radians. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important to note that the phase difference for an entire wave is 360 degrees. So you can work everything out based on that. So you can work out that the first one, which is 20 centimeters, is half the wave, because the wave is 40 centimeters. So therefore the phase difference is half of 360, which is 180 degrees. Now the 40 centimeters is one complete wave, so it's 360 degrees, or 0 degrees, because it's gone back to where it starts again, because you can imagine a bit like a circle going all the way back round. So you can also have it to be 0 degrees. Now at 80 centimeters, that's in fact 2 wavelengths, so therefore that's 720 degrees. You could also say it's back to 0 again, because it's just gone around the circle again twice. Now in this next question, you're going to have to work out how big the difference is. Now again, remember, one wavelength is 360 degrees. So if you've got a phase difference of 90 degrees, that's a quarter of a wavelength. So that is a quarter of 1.60 meters, which is 0.40 meters or 40 centimeters. Now the next one's 540 degrees. So again, 540 degrees is actually going to be 1.5 waves. So therefore it is 1.6 plus 0.8, because it's 1.5. So it's 2.4 meters. Now, in theory, the displacement, by the way, because again it's gone back round to the start again, would actually just be 0.80 meters as well. Now, 5 pi radians. Now, this is an important idea to understand, that whilst the phase difference of one wavelength is 360 degrees, that is also equal to 2 pi radians. So 5 pi radians is actually going to be 2.5 waves, because we've gone round it twice and once more, because it's 2 pi for every one wavelength, so therefore it is 4 meters. The next question says, looking at the figure below, this shows you the relative intensity between two Polaroid filters. Explain why maximum intensity occurs at 0 degrees and 180 and 360, and a minimum between 90 degrees and 270 degrees. And then second question, a student holding a polarizing filter in front of a laptop screen and then rotates it. At a particular angle, the laptop screen appears to go dark. So firstly, suggest what you can deduce about the nature of the light emitted from a laptop screen from the student's observation. Then explain how the laptop screen can be viewed once again through the filter. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing you've got to understand is this is regarding polarization. So at 0, 180 and 360, the two Polaroids are aligned with each other. So you get the same orientation of the wave being polarized. So that means all of it will go through both the filters, so you get a maximum intensity. At 90 and 270 degrees, your two Polaroids are polarizing two waves which are perpendicular to each other. So whilst it'll go through one of the Polaroids, it won't go through the other Polaroid, so the intensity will fall to 0. Now in 2.1, what can we deduce about the nature of light in the fact that as the polarizing filters in front of the laptop screen, it'll change the amount of light going through it? Well, it tells us that it's being polarized, so therefore it must be playing polarized. Now, how can you get your laptop screen to be viewed again through the filter? Remember, if you've got two filters, you can only get maximum intensity when the two Polaroids are parallel with each other. Now, from the orientation you can see in the question already, they must be perpendicular to each other. So therefore, to get from perpendicular to parallel, it takes a 90 degrees rotation to do so. So you must rotate it 90 degrees. The next question says, describe two similarities between progressive and stationary waves. Then describe the phase difference between the two waves that form a stationary wave, firstly at a node, then secondly at an antinode. Then a standing wave has adjacent nodes 30 centimeters apart. Calculate the wavelength in meters of the progressive waves responsible for this standing wave. And then finally describe how the amplitude of a standing wave varies from one node to the next. So pause the video now. Then unpause the video when you want to go through your answer. Right, so the first question is pretty much asking you, what are the common properties of all waves? So the common properties of all waves you've got to remember are that all waves are comprised of oscillations and vibrations. The second thing is all waves will have the common properties of frequency, time period and amplitude. You could also substitute wavelength in there for frequency as well if you wanted to. Now, if you've got two waves and they form a stationary wave and there's a node, well, a node means no energy, no amplitude, no wave, so they've got to be an antiphase. So when they add together, when they superimpose, they completely cancel each other out. And for the antinode, you've got a maximum amplitude, a maximum energy, a maximum wave, so the two waves must reinforce each other, so they must be in phase with each other. Now for the next question, for question 3, it's important to note that two adjacent nodes, adjacent meaning next to, two nodes are always half a wavelength apart. So if the two nodes are 30 centimeters apart, it tells us that half a wavelength is 30 centimeters, so a full wavelength is 60 centimeters or 0.60 meters. Now you've got to remember that the amplitude at a node is 0 because a node is no energy, no amplitude, no wave. As you move away from the node, the amplitude will increase and increase and increase. It then hits a maximum amplitude at the antinode before then decreasing again back down to 0 at the next node. The next question says, the stationary wave below is produced at a frequency of 120 Hz. The length of the string is 0.36 meters. Firstly, state the first harmonic of the string. Secondly, determine the wavelength of the original progressive wave. And then sketch the pattern produced if the frequency changes from 160 Hz to then 100 Hz. So, pause the video now, then unpause the video when you want to go through your answer. Right, so what you can note is when you've got a standing wave, the number of antinodes, which is the places of maximum displacement, is equal to the number of harmonics. So you can see here that there are 3 antinodes, so therefore it's the third harmonic. So to work out the frequency of the first harmonic, you take the frequency of the third harmonic and you divide it by 3. So 120 divided by 3 is 40 Hz. Now you can see in this particular picture that the entire length of the string is 0.36 meters, but it's actually 1.5 waves because you have 2 antinodes or 2 deviations from 0 to maximum amplitude in one wave. There's 3 of them, so that tells you got 1.5. So if there's 1.5 wavelengths in 0.36 meters, well therefore in one wavelength it's 0.24 meters. Now, how would the pattern change if you went to 160 Hz? Well, you'll notice that the harmonics are produced in the multiples of the first harmonic. The first harmonic, in this case, is 40 Hz, so I'll go multiples of 40. 40, 80, 120, 160. So therefore 160 is the 4th harmonic, so therefore you would sketch the 4th harmonic. So you'd have 4 antinodes in your standing wave. Now for 100 Hz, 100 is not a multiple of 40. It goes 40, 80, 120, 140, 160. So at that point, it's not a multiple of the first harmonic, so you would not get a standing wave pattern formed at 100 Hz. The next question says, explain why it's necessary to use monochromatic light along with a single slit and a double slit to produce a stable interference pattern for light. Then the next question says, the following measurements were taken during a double slit experiment. The separation between the slits is 0.6 millimeters. The separation between adjacent bright fringes is 1.4 millimeters. The distance from slit to screen is 1.6 meters. And from this, calculate the wavelength of the light used. Then for number 3, explain the effect on the interference pattern seen on the screen for a double slit experiment when A light source with a longer wavelength is used. Secondly, B, the slit separation is doubled. Thirdly, the distance from slit to screen is increased by a factor of 3. And then fourthly, a light source with double the frequency is used. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important to note what waves have to be to get a stable interference pattern, and that is the waves must be coherent. So that means they've got a constant phase relationship, the same frequency, the same wavelength, the same time period. And then using a monochromatic source, a single slit and a double slit will give you two coherent sources of light, so they will form a coherent and stable interference pattern. Now for this next one, we've got to look on our equation sheet, and we looked at it for a double slit, for Young's double slit, the wavelength is equal to WS over D. So you can then pop in the values. Now you'll notice from the values that you've got millimeters and meters. So it's all going to be the same unit. So you convert millimeters into meters by times and by 10 to the minus 3. You pop it all in and you get 5.3 times 10 to the minus 7 meters. Now that makes sense because you should know that visible light has approximately a wavelength of 500 nanometers, which is about 5 times 10 to the minus 7 meters. Now in this next question, you've got to look at this equation for the double slit experiment and see how the values would change. So from the equation, lambda equals WS over D, so therefore we can say that W, okay, which is going to be the slit spacing, is going to be equal to lambda D over S. Well, that tells us that as the wavelength increases, the fringe space will increase. If the slit separation was doubled, we can therefore see that S will half. So you can see straight away, because it's an inversely proportional relationship. Again, we know that W is directly proportional to D from the equation. So as D increases by a factor of 3, W will also increase by a factor of 3. Then the last one, you've got to remember that frequency isn't in the equation, but wavelength is. And you should know that wavelength and frequency are inversely proportional from the equation C equals F lambda, and C is a constant, so therefore F and lambda are inversely proportional to each other. So if you double the frequency, it tells you the wavelength halves. We know that wavelength is proportional to W, so if the wavelength halves, well therefore W will half as well. The next question says, the constant frequency signal from a signal generator is fed into two loudspeakers placed 1.5 meters apart. A girl who is 8 meters away from the speakers walks across in a line parallel to the line between the speakers. She finds that there's a distance of 1.2 meters between successive spots where the sound is very quiet. So calculate the wavelength of the sound. Then explain what is meant by the term superposition. Then, in a Young's double slit experiment using yellow light of 500 nanometer wavelength from a sodium discharge tube, a student sets up a screen 1.8 meters from the double slit. He measures the distance between 12 fringes as 16.8 millimeters. From this information, calculate the separation of the slits. Then state the effect of using slits of a narrower width but the same separation, and using slits with a smaller separation but of the same width. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you've got to use the equation lambda equals WS over D, because we're trying to work out what the actual value is going to be for the wavelength of the source. So you can see that we've got W, which is the separation between the values. So therefore, you can see it's going to be 1.2 times by the slit separation, which is going to be 1.5, because that's where the two speakers are, divided there by the distance between the two, so the distance between where it's observed when the speakers are, so that you get 0.23 meters. Now superposition, what is that? It is the summing of the displacement of two or more waves which are coherent with each other. Now in question 2.2, once again, we're going to use the double slit equation. So W equals lambda D over S. We will pop in the values. Now firstly, nanometers turns into meters. So it's 590 times 10 to the minus 9. You've got to also be very careful when we're working things through here, because you'll notice that the distance between the fringes is measured to be 16.8 millimeters. So what you could either do is multiply the top by 12 or divide the bottom by 12, because you're doing 16.8 as 12 of them, so 16.8 divided by 12 will give you one of them. Now remember that 16.8 is in millimeters, so it's going to be converted into meters by times and by 10 to the minus 3. So we get our answer to be 6.3 times 10 to the minus 4 meters. Now, what would happen if we used a slits of narrower width? Well, you'd see more fringes seen on the screen, because you can see from the equation about what's going to happen with W equals lambda D over S. And again, if you use slits with a smaller separation with the same width, well again, W equals lambda D over S. So therefore, if S goes down, well that tells you W will go up, because they're inversely proportional from the equation. So therefore, the fringes are now going to be further apart. In our next question, it says the refractive index of a plastic block is 1.47. What is the speed of light in this plastic? The second question says calculate the relative refractive index of a water to glass boundary. The refractive index of water is 1.33 and the refractive index of glass is 1.50. Then question 3, calculate the refractive index of material 2, given that material 1 has a refractive index of 1.1. And then question 4, calculate the angle of incidence of the light ray in the diagram stated below. So pause the video now, then unpause the video when you want to go through your answers. Right, so how to answer this first question? Well, you've got the refractive index and you can link that into speed by saying speed is equal to the speed of light in a vacuum divided by the refractive index. So it's 3 times 10 to the 8 over 1.47, 2.04 times 10 to the 8 meters per second. The second question, working out relative refractive index, it's going to be equal to N2 over N1. You've got N2, the refractive index it goes into, which is 1.50. You've got N1, the refractive index of the material it starts in, 1.33. So the answer is 1.13. In this next question, you've got two angles and you've got one refractive index, so you can use Snell's law. So N1 sine theta 1 equals N2 sine theta 2. Pop in all the values given in the question and you can work out N2 to be 1.44. That also makes sense because you can see that the angle of refraction has actually decreased. So therefore, you can tell that in that material, okay, it's in fact gone down. Okay, so that's an important idea to note. And then finally, in question 4, once again, you'll be given two refractive indexes. You've been given one angle, so you can use Snell's law again to work out what this angle is going to be, and it's 63.2. Once again, that makes sense. It's got a bigger angle than what it goes into because it's traveling faster in the original material because the refractive index is lower. The next question says, an optical fibre consists of a core, cladding, and outer sheath. Firstly, state the purpose of the outer sheath in an optical fibre. And then for one fibre, the speed of monochromatic light in the core is 1.97 times 10 to the 8 meters per second, and the speed in the cladding is 2.03 times 10 to the 8 meters per second. From this information, calculate the critical angle for this light at the interface between the core and the cladding. So pause the video now, then unpause the video when you want to go through your answer. Right, so you should just know what the purpose of the outer sheath is. So it's to prevent damage to the optical fibre, it protects the fibre, and it also strengthens the fibre as well. Now, to work out what the critical angle is going to be, you've got to work out the relative refractive index between the core and the cladding. So you do the speed that is going to be in the cladding divided by the speed that it is in the core, because it's what it's going to divided by what it's in. So you get 1.03, and then we know that sine critical angle is 1 over n. So it's going to be 1 over 1.03. So we get our critical angle to be 76 degrees. Let's have a look at some checkpoint questions. So in this first question, now we're looking at more applied circumstances to the concepts of this module. In testing a particular type of guitar string, a string is stretched and vibrated for a long period of time using a mechanical vibrator as shown below. The right-hand end of the string is fixed. A stationary wave is produced on the string and the string vibrates in two loops. Firstly, state the conditions that are necessary for a stationary wave to form on the string. Explain how you would know that the wave on the string is transverse, and then compare the amplitudes and phase of oscillations of points A and B on the string. So pause the video now, then unpause the video when you want to go through the answer. Right, so in this first question, it's asking you what do you need for a stationary wave to form. So you need a reflection of a wave, so there's two waves in opposite directions, and that the frequency is constant, or there's the same frequency, same wavelength, and a constant phase difference. You've got coherency between the two waves. The next question is asking you to define what we mean by a transverse wave, and that is when the displacement or the oscillation is perpendicular to the propagation of the energy of the wave. And then finally, what is the difference in the amplitude and phase of points A and B? Well, firstly, you'll notice that A has a bigger amplitude than B because its position is further away from the equilibrium position of the vibrator than B is, but also that A is pi radians out of phase with B, because you'll notice they're on completely opposite points of the wave oscillation. One is above by the certain value and one is below by that same certain value, so they're completely out of phase. So they've got a difference of half a wavelength, which when you put it into a phase difference is pi radians. The next question says, when a note is played on a violin, the sound it produces consists of the fundamental, which is the first harmonic, and many overtones, the higher harmonics. Figure 1 shows the shape of the string for a stationary wave that corresponds to one of these overtones. The positions of maximum and zero displacement for one overtone are shown. Points A and B are fixed, points X, Y, and Z are points on the string. Firstly, describe the motion of point X, then state the phase relationship between X and Y and X and Z, and then the frequency of this resonant frequency is 780 Hz. Show that the speed of the progressive wave on the string is 125 meters per second, and then calculate the time for the string at point Z to move from a maximum displacement back to zero again. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, it's the idea of a stationary wave, and then it's going to oscillate a bit about the equilibrium position from positive to negative. So you can see it's going to vertically oscillate. Now, when you look at X and Y and X and Z, you'll notice that X and Y are out of phase because they are oscillating in opposite directions of your stationary wave at that point, but X and Z are oscillating in the same direction, so they are in phase. Now, in the next question, speed is equal to frequency times by wavelength. Now, you can work out what the wavelength was. It was 0.16 meters because the entire length of the string was 0.32 meters, but that was for two waves, so one wave was 0.16. So you multiply that by 780 Hz to get to 124.8 meters per second. Now, you should also know that the time taken to go from maximum displacement to zero displacement is going to be the time it takes to move a quarter of a wave, 90 degrees displacement. So you can work out what the time period is by doing t as 1 over f, so 1 over 780, and that's one whole cycle, so it's a quarter of that, which is 3.2 times 10 to the minus 4 seconds. The next question says the violinist presses on the string at C to shorten the part of the string that vibrates. Figure 2 shows that the string between C and B are vibrating in its first harmonic. The length of the whole string is 320 millimeters and the distance between C and B is 120 millimeters. Firstly, state the name given to the point on the wave between C and B. Secondly, calculate the wavelength of the stationary wave. Then thirdly, calculate the frequency of the first harmonic. The speed of the progressive wave remains at 125 meters per second. So pause the video now, then unpause the video when you want to go through your answer. So the first question is asking you, what do you give the name to the maximum displacement in a stationary wave? And that is an antinode. Now, how do you work out the wavelength? Well, we can see that that here you've got the distance to be 240 millimeters for the first harmonic, but that's only half the wave, so you've got to double that and convert it into meters, so it's 0.48 meters. The next one says work out the frequency of the first harmonic, and you've got the speed to be 125 meters per second. Well, frequency is speed over wavelength, pop in the values and you get 260 Hz. The next question says a transverse wave travels on a stretched chord from left to right. Figure 4 shows at a given instance the shape of the chord. The frequency of the wave is 2.4 Hz. A, B and C are particles on this rubber chord. Firstly, determine the speed of the wave. Secondly, calculate the phase difference between points A and B in degrees. Then thirdly, describe and explain the direction in which A would move as the wave travels a very short distance. So pause the video now, then unpause the video when you want to go through your answer. Right, so this first one, you can see how long a wavelength is. So you can see firstly from the information given to you that there's 1 meter for 1 1/4 waves. So therefore 1 wavelength is 0.80 meters. We know speed is frequency times by wavelength, so it's 2.4 times by 0.80, 1.92 meters per second. Now again, the phase difference, it is going to be how much it changes in the entire wavelength, so 0.30 over 0.80 times by 360 degrees, because there's 360 degrees in one wavelength, so it's 135 degrees. Now to work out the direction A would move in as it travels a short distance, look at the pattern that the wave is pushing out, because it's going to be a transverse wave. So look at how A would happen as it moves across to the right, because it's moving from left to right. So therefore A would move downwards because the rope is moving in a downwards direction. The next question says, figure 6 shows the surface of a water in a ripple tank at a given instance. Firstly, draw the diagram and show the wavelength of the wave. Secondly, draw the diagram and show the amplitude of the wave. Thirdly, compare and contrast the motion of particles P and Q as the wave travels to the right. And then at 1.4, the distance between P and R is 2.1 centimeters. The frequency of the wave is 20 Hz. Calculate the speed of the wave. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, what is the wavelength? It is from peak to neighbouring peak, or twice the distance of PQ. So it's after two antinodes, you can think of it in that term, and back to the start again. I know it's not an antinode in this case because it's not a stationary wave. Then the amplitude is from the equilibrium position to maximum displacement, either the peak or the trough. Now, what's going to happen to P and Q? Now, both particles have the same amplitude and the same frequency, and there's a phase difference of about 180 degrees between the motions of P and Q. You'll see that because follow the wave along. So P is actually going to be going upwards because it's going to follow that pattern along, whilst Q will be going downwards because you're following that pattern along as it's going to the right. Now, if the distance between P and R is 2.1 centimeters, we can say that therefore the wave is going to be 2.8 centimeters, because you can see P to R is in fact it's going to be 3/4 of a wave, so therefore one whole wave is going to be 2.8 centimeters. So we can say 2.8 centimeters, or 0.028 meters, times by the frequency 20 Hz is equal to 0.56 meters per second. Now, our next question says, consider points D and E on the screen. State and explain what you expect to observe at D and E. And then, in a double slit experiment using light from a helium neon laser, a student obtained the following results. The width of 10 fringes is 1.5 centimeters. The separation of the slits is 1 millimeter. The slit to screen distance is 2.40 meters. What is the wavelength of the laser? So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can see that D is going to be a dark fringe. Why is it going to be a dark fringe? Because you can see that the rays from slits 1 and 2 will have a path length difference of 1.5 wavelengths. And so when you've got a half a wavelength difference between two of the path, it's going to be a dark fringe, whilst E has a path difference of 2 wavelengths, and when it's an integer difference, it's a bright fringe. Now, the next question, you've got to remember, you've got to actually firstly convert the width of the 10 fringes into one fringe. So it's 1.5 centimeters divided by 10. Then you've got to convert that into meters. You've got to convert the separation of the slits into meters. You pop it into the equation, lambda equals WS over D, and you get 6.3 times 10 to the minus 7 meters. That looks like it's going to be right because it's about 600 nanometers. The next question says, describe how the interference pattern would change if a laser emitting green light was used in an experiment in place of a laser emitting red light. Then explain why it's better to measure the separation between multiple fringes to determine the fringe separation rather than between adjacent fringes. Then a helium neon laser of wavelength 632.8 nanometers is used to form an interference pattern from a double slit with a slit separation of 0.50 millimeters. Calculate the separation between the adjacent fringes. Then the following measurements were taken during this double slit experiment using light with a wavelength of 610 nanometers. The separation between the slits is 0.40 millimeters. The separation between the adjacent bright fringes is 1.8 millimeters. What's the distance from slit to screen? So, pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, if you have red light instead of green light, the separation between the fringes will be smaller because green light has a shorter wavelength than red light. We know that W equals lambda S over D. So if lambda goes down, well then W goes down, so the separation between the fringes is lower. Why do you do multiple slit spacings? Because it reduces the percentage uncertainty, because the measurement for multiple fringes will be bigger than the measurement for just one fringe. The next question, we use lambda equals WS over D, so W equals lambda D over S. Convert the nanometers into meters, convert the millimeters into meters, pop in all the values, and we get 1.3 times 10 to the minus 2 meters. Once again, we do the same equation, with this time we make D the subject, as you can see on the screen. We convert the millimeters into meters, we convert the nanometers into meters, and we get our answer to be 1.2 meters. The next question says, consider the equation d sine theta equals n lambda. How will the diffraction pattern change if the wavelength of the wavelength is increased, The diffraction gradient is changed from 1 with more lines per centimetre. And then the second question says, a student is trying to make an accurate measurement of the wavelength of green light from a mercury lamp of wavelength 546 nanometers. Using a double slit of separation 0.50 millimeters, he finds he can see 10 clear fringes on a screen at a distance of 0.80 meters from the slits. The students can measure their overall width to within 1 plus or minus 1 millimeter. He then tries an alternative experiment using a diffraction gradient that has 3,000 lines per centimeter. The angle between the two second order maxima can be measured within plus or minus 0.1 degrees. What will the width of the 10 fringes that he can measure in the first experiment be? What will the angle of the second order maxima in the second experiment be? And suggest which experiment you think will give a more accurate measurement of lambda. So pause the video now, then unpause the video when you want to go through your answer. Right, in the first one, we can say that d sine theta equals n lambda. So lambda, okay, is increased, so therefore theta will increase, so therefore the maxima are more spread out. In this next one, we know that d is equal to 1 over the number of lines per centimetre or per metre. So if there's more lines per metre or per centimetre, d will go down. So from the equation that tells us theta will go up, so therefore the maxima are more spread out. In question 2.1, how can you work it through? Well, you can use the equation lambda equals ws over d, so w equals lambda d over s. Pop in all the numbers and you'll work it through to be 0.87 millimeters. So therefore, in total, 10 fringes will have a value of 8.7 millimeters, and the student will measure that to be 9 millimeters with the uncertainty of the ruler considered. Now, the angle of the second order maxima, we can say that the separation of the lines in the gradient, d, is equal to 1 over n, so it's 1 over 3,000 centimeters, so it's 3.3 times 10 to the minus 6 meters. We can then make sine theta the subject and therefore work out theta to be 19.1. Now, which one will give us a more accurate value? Well, for the double slit experiment, you measure a width of 9 millimeters, so therefore you would do plus or minus 1 over 9 to get that value, and then for the diffraction gradient you'd be using a value of 19, so therefore it will be plus or minus 0.1 over 19, and then times by 100 in both cases, work out your percentage uncertainty. As you can see, the diffraction gradient 0.1 over 19 will give us a much smaller answer, so therefore it's more accurate. And in addition, when you're using diffraction gradients, the images are brighter and more well defined, so it's easier to measure more accurately as well. The next question says, white light is incident normally on a diffraction gradient with a slit separation of 2 times 10 to the minus 6 meters. Calculate the angles between the red and violet ends of the first order spectrum. The visible spectrum has wavelengths between 400 nanometers and 700 nanometers. Then explain why the second and third order spectra overlap. So pause the video now, then unpause the video when you want to go through your answer. Right, so how to answer this question? Well, we're doing diffraction gradient, so we've got to use the equation d sine theta equals n lambda. So for each one, you rearrange it and make theta the subject. So sine theta equals n lambda over d. It's the first order, so n equals 1. We've got the wavelength, so we can work it through, and we've got d from the question as well. So for red, it's 20.5. For violet, popular number is 11.5. So the difference between the two of them is 9.0 degrees. Now, while the second and third order spectra overlap, well, the third order maxima for the violet is deflected through a smaller angle than the second order maxima for red light, because you've got to consider the different wavelengths of each of them as well. So therefore, it would work through that they would actually overlap in terms of angles. Now, the next question says, figure 7 shows 3 transparent glass blocks, A, B and C joined together. Each glass block has a different refractive index. Calculate the speed of light in glass A, where the index of glass A is 1.80, and then show that the angle theta is about 30 degrees. So pause the video now, then unpause the video when you want to go through the answer. Right, in this first one, we want to work out the speed of light in the material. We have its refractive index, so we say that it's going to be equal to the speed of light in a vacuum divided by the refractive index, so it's 1.67 times 10 to the 8 meters per second. Now, if you look on the screen here, you've got both refractive indexes, because you know the refractive index of air is 1. You've worked out the refractive index of glass, so we can do n1 sine theta 1 equals n2 sine theta 2, work it all the way through, and we get 31.9 degrees. That makes sense. It's going to be a smaller angle because it should be going slower, so it's going closer to the normal because it's going to a high refractive index. Let's have a look at some examination style questions on the wave topic. So, first question, a student connected a signal generator to the loudspeaker and placed the loudspeaker near one end of a long tube containing sand. The student adjusted the signal generator until the sand collected in small heaps as shown. Firstly, explain why the sand collects in heaps. Secondly, the student determined the distance d between the centres of adjacent heaps and described the procedure she should follow to determine an accurate value of d. And then next, assess whether the experimental data is consistent with the value for the speed of sound of 340 meters per second. The signal generator frequency is 3.25 kHz and d is 5.1 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, why is it collecting heaps? Well, it's the idea it's forming a stationary wave. So you've got a standing wave set up in the tube because there's interference where the sound wave hits off the back of the tube and comes back. So you get a constructive interference where the amplitudes are maximum, you get destructive interference where the amplitudes are minimum, and the sand is therefore displaced between antinodes and nodes. Now, how do you get an accurate value for measuring d? Well, you need to be measuring multiple values because dividing measuring over a bigger value loads your potential uncertainty. You then divide by the number of gaps to work out your average, and then you repeat and calculate an overall average. Now for this next one, you'll have seen very quickly that we need to work out with the speed. So we know that speed is equal to frequency times by wavelength, and wavelength is double the distance between two adjacent nodes. So we convert 5.1 centimeters into meters, we then double it to get our wavelength, we multiply it by 3.25 times by 10 to the 3, and we get 332, which is close to the value of 340 meters per second. The next question says, the photograph shows a stringed instrument called a cello being played with a bow. A standing wave forms on a cello string when the bow moves across the string. Deduce whether a thicker string will produce a note of higher or lower frequency compared with a thinner string. Assume each string is the same length and at the same tension. So pause the video now, then unpause the video when you want to go through your answer. Right, what you should see by looking at the equations given to you on the equation sheet, that ultimately when you consider everything that stays constant, V is going to be equal to the square root of T over mu, where mu is the mass per unit length. So if you've got a thicker string, mu is going to be a bigger value, T is going to stay constant, so therefore if T is staying constant and mu is getting bigger, V will therefore be getting smaller. Now we know V equals F lambda, and the wavelength lambda will stay constant. So therefore, if we are going to maintain that value of V, that tells us we've got to have a lower frequency with that thicker string. And you can also think to yourself, if it's a thicker string, it's harder to move, it's going to need more energy, so therefore its frequency of vibration will be lower. The next question says the speed of wave on a string can be described with the equation V equals the square root of T over mu. The string has a length of 0.69 meters and has a mass of 9.0 times 10 to the minus 3 kilograms. The wave is traveling along the string at a speed of 203 meters per second. What is the tension in the string? Then when the string is fixed at both ends and plucked, a stationary wave is produced. Explain briefly in terms of superposition of waves how the stationary wave is produced. Then 1.3 says the string is vibrating at a fundamental frequency of 270 Hz and produces the stationary wave pattern shown in 9.A. Figure 9b shows the same string vibrating in its third harmonic. Determine the frequency of the third harmonic. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, you can work out mu, or mass per unit length, by doing the mass over the length. We can then pop it into the equation V equals the square root of T over mu. We can therefore work it all the way through, and therefore we get our answer to be 540 newtons. Now, how will you get a stationary wave? Well, the wave is reflected from each end. They're coherent, they'll interfere to create maxima and minima. Now, you've also got to know that for the next question, the frequency of the third harmonic is going to be the third multiple of the first harmonic, which is 270. So it's 3 times by 270, so it's 810 Hertz. The next question says, a student is carrying out an experiment to investigate the interference of sound waves. Two identical loudspeakers, L1 and L2, are connected to a signal generator as shown. The sound level meter is moved from A to B and a series of maxima are detected. The sound waves emitted from the loudspeakers are coherent. Explain what is meant by the term coherent. Then explain in terms of waves how a maximum is produced. Then the wavelength of the sound wave is 0.400 meters. The distance from L2 to the third order at point P is 6.00 meters. Determine the distance from L1 to P. Then a second student in the room is wearing a pair of active noise cancelling headphones. The student switches this function on. The sound level from the loudspeakers heard by the student decreases significantly. Name the type of interference that the headphone uses to reduce the sound level. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, how are they coherent? Well, they've got a constant phase relationship, same frequency, same wavelength, same velocity. In terms of a wave, how is a maximum produced? When they meet in phase, or they've got a path difference of integer lambda. The next one, you can see that the path difference is n lambda because it's a coherent. It is a bright fringe. It's a maxima. It is a overall added together. Now that happens when you got an integer wavelength difference, and it's the third maxima, so it's 3 times by the wavelength difference. So it's 3 times by 0.40. But the path difference is also the difference of the two waves. We know that one of them takes a path of 6 meters. The other one must have a difference of 1.2 to get the actual difference there, because we know that's the path difference required. So therefore the other one is 4.80 meters. And then the interference to reduce the sound level would be destructive interference. The next question says, lighthouses are located along coastlines to aid navigation. A lighthouse emits an intense beam of light. In clear weather, the beam is visible for long distances, but in foggy weather, the visibility of the beam is limited. The beam is refracted by water droplets in the air. A light ray in the beam is incident on a spherical water droplet with an angle of incidence of 40 degrees. The ray passes through the droplet and meets the water-to-air boundary at x as shown. Deduce whether the ray leaves the water droplet at point x, and the speed of light in water is 2.25 times 10 to the 8 meters per second. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you work this through? Well, firstly, work out the relative refractive index, so you got both speeds of light in the particular media. So you can say air to water is 3 times 10 to the 8 over 2.25 times 10 to the 8, so it's 1.33. We can then work out what our angle is going to be by doing n1 sine theta 1 equals n2 sine theta 2. Remember, n1 is 1 because it's air, so therefore theta 2 is 29 degrees, and therefore we can work out what the critical angle is by doing sine critical angle is 1 over n, so you can work it through like that. So therefore the critical angle is going to be 49 degrees. The angle of refraction is 29 degrees, so therefore it will refract through, so therefore you can see what's going to take place. Now the next question says calculate the largest angle theta to the axis at which the light can travel for long distances through the core of the multimode fibre if the refractive index of the core is 1.574 and that of the cladding is 1.550. Then explain what would happen to light entering the fibre at an angle to the axis greater than the angle calculated at 1.1. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, firstly, you can work out what the critical angle is going to be. So therefore you can say sine critical angle is going to, sine C there is going to work it through to be 80 degrees, like so. So therefore by doing your mathematics there, so the sine critical angle you work through to be 80 degrees, and therefore if that critical angle, which is going to be the angle between the core and the cladding, is 80 degrees, from the similar triangles you can see below, it's going to be 90 minus 80, so it's 10 degrees. Now if light entered at the angle greater than that, well therefore your refraction wouldn't happen, so therefore some reflection or some light would escape from the core and some will go into the cladding. So finally, figure 1 shows 2 rays of light, A and B, travelling through a straight optical fibre. Calculate the speed of light in the core of the optical fibre. The absolute refractive index of the core of the optical fibre is 1.6. Then the overall length of the optical fibre is 0.80 kilometers. As shown in figure 1, ray A travels down the centre of the core of the optical fibre. The path of ray B has an overall length of 0.92 kilometers as it travels down the core. Ray A and ray B enter the fibre at the same instance. Calculate the difference in time taken for ray A and ray B to travel through the core of the optical fibre, and then explain how an optical fibre prevents this time difference from occurring for rays such as A and B in figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we know how we can work out the speed because we've got the absolute refractive index. So therefore, the absolute refractive index is the speed in a vacuum divided by the speed in the material. Rearranging the speed in the material is 1.9 times 10 to the 8 meters per second. That's less than the speed of light. It makes sense. The next one, we can see that the path difference is actually going to be 120 meters or 0.12 kilometers from the overall length to the path length of ray B. You can see that's the difference there. So the time difference is therefore going to be the difference in this path divided by the speed, which for both of them is going to be 3 times 10 to the 8 because it's light. So therefore it's 120 over 3 times 10 to the 8. So it's 6.4 times 10 to the minus 7 seconds. And then finally, how can it prevent this? Well, the refractive index will vary across the core and also be a maximum at the center. So therefore it tells us that rays will travel slower in the center and rays will travel faster at the edge. So therefore they hopefully won't have this time difference. So that brings the end to our revision session today. So if we're being successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for AQA A-Level Physics in the Waves section. Thank you so much to listen to this revision session on paper 1 for AQA A-Level Physics on the topic of waves. Thank you so much and have a lovely day. Hello and welcome to this revision session where we're going to look at the topic of waves in AQA A-Level Physics. So in today's revision session, our learning objective is to answer examination questions on the waves topic of A-Level Physics. So if we've been successful and we've learned in this lesson, we should be able to answer A-Level Physics examination style questions, you should be able to assess your understanding on A-Level Physics, and finally understand what topics we need to improve upon for A-Level Physics. So how do you prepare for this revision session? So when completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side, and then on the left hand side write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure you write in full sentences and show your full working out, whilst in the right hand side write down any pieces of information which you find useful or any hints and tips on answering questions from this revision session. At the end of the revision session, I would advise that you write up these notes into a revision sheet for you to revise independently. So what tips do you have for revision? So how can you be independently revising your A-Level Physics? So the first step is always to use your revision guides, use the class workbooks, your prep notes, your textbook to learn the key ideas of the course, learn the key facts. Now you might want to do this by making mind maps or writing notes out yourself. The second step will be to test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you might want to do this by making your own cue cards. And then finally, practice examination style questions by using examination prep books, homework books, supervised study books, additional workbooks to help you answer examination questions and then mark your own work. And to do this, you might want to download your own examination papers to do this. So the 3 steps of learn the key facts, testing yourself, and then practicing examination questions are how you should be revising physics independently. So let's have a look at some multiple choice questions on waves. So let's look at the following question. In the derivation of the diffraction gradient equation n lambda equals d sine theta, a diagram similar to one below can be used. Which of the labelled angles alpha, beta or gamma is equivalent to the angle theta in the equation? So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to understand is that when you're looking at the equation n lambda equals d sine theta, okay, that the angle alpha is the angle given the equation, because this angle of theta is the angle measured from the normal of the slit. But beta is also a possible answer, because if you consider similar triangles, you notice that alpha and beta are actually going to give you the same value. So the answer there was B. Next question. A pulse of white light passing along the axis of a straight optical fibre. The pulse is broadened when it leaves the optical fibre. So what causes this particular effect? So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to understand what absorption, attenuation, material dispersion and modal dispersion are. Now straight away, absorption and attenuation won't be the correct answer because we're considering the idea of the pulse actually broadening, which means that the wave is spreading out, the signal is spreading out. Now the answer is C, because material dispersion causes the signal to spread out as it travels through a material, which then leads to the concept of pulse broadening. Our next question is that light crosses the boundary from air into a substance that has a refractive index of 2. Now what happens to the speed, the frequency and the wavelength of the light as it crosses the boundary? So pause the video now, then unpause the video when you want to go through your answer. Right, now the first thing you've got to remember is that in refraction the frequency remains constant. So the answer is either going to be A or B. Now your answer in this instance is A, because if an object is going to a higher refractive index, then it must be slowing down because it's going into a more optically dense material. Now we know that the actual denseness optically of the material has doubled because air has a refractive index of 1 and this substance has a refractive index of 2. So if the density optically of the material has doubled, then the wave is going to slow down and therefore its speed will halve. Now the wavelength will also halve due to the wave speed equation, because we know wave speed is equal to frequency times by wavelength. So if the frequency remains constant and the speed halves, it means the wavelength must halve as well. Let's now have a look at our next question. A stationary wave forms on a string when progressive waves are reflected at fixed ends. For a real string, energy is transferred from the progressive waves when they are reflected at the fixed ends. The effect of this energy transfer on the stationary wave is that. So pause the video now, then unpause the video when you want to go through your answers. Now the important thing you've got to note is that when they're reflected in the real world, you won't get this exact interference pattern where you'll get complete nodes and you get complete antinodes. So it's not that the nodes and antinodes no longer form, but rather the answer would be B, that the nodes would not be positions of zero amplitude because you won't actually get the two waves completely cancelling out, so they wouldn't go to exactly zero. So our answer in that instance was B. Let's have a look at our next question. Ray X is incident on one slit and ray Y is incident on another slit of a double slit arrangement as shown below. A fringe pattern is not observed on the screen. What is the possible explanation for this? So pause the video now, then unpause the video when you want to go through your answer. Right, now it's important again to note that to get a fringe pattern on a screen, that the waves must be interfering with each other to cause this fringe pattern. Now, to get waves to interfere, you need to have the rays be coherent with each other. Now, the definition of coherent is that the waves have a constant phase difference and they have the same wavelength / frequency. So the answer here is X and Y do not have the same wavelength, so you can't have coherency, so you don't get an interference pattern forming. So our answer here is B. Next question. Light of wavelength 500 nanometers is incident on a double slit and the resultant fringe pattern is shown below. V is the central bright fringe and the dark fringes are shown shaded. What is the path differences that results in fringe W? So pause your video now, then unpause the video when you want to go through your answer. Right, so it's important to note that W is a second order dark fringe. So this means that the two waves must be out of phase with each other and so must have a path difference of an odd number of half wavelengths. Now because this is a second order fringe, as we'll notice because it's not one of the central ones but it's a second order one, the path difference is therefore going to be 2.5 wavelengths, because our equation to work out the path difference of which causes destructive interference is going to be 2n plus 1 over 2 wavelengths. So therefore that tells us that we're going to have 2.5 wavelengths, which gives us 1250 nanometers, resulting in our answer of A. Let's now have a look at a few longer style questions to do with waves. So the first question is, laser light is incident normally on a diffraction grating. The diffraction grating has 250 slits per millimeter. A third order maximum is observed at an angle of 29 degrees to the central maximum. Calculate the frequency of the laser light. So pause the video now, then unpause the video when you want to go through your answer. Right, so first thing you've got to note is that in the equation you want to be using n lambda equals d sine theta, but d needs to actually be calculated very carefully because it's not 250. The first thing you would need to do is you need to work out what the actual distances between the two slits are. So if there's 250 slits per millimetre, the distance in metres between two slits is 1 over 250 times 10 to the 3, because you've got to work out how many slits are actually in 1 metre, so it's 250 times 10 to the 3. So therefore you get your answer, you get your value for d, you then plug this into the equation n lambda equals d sine theta, and you make lambda the subject. You say lambda equals d sine theta over n. We know what theta is. It's 29 degrees from the information given in the question. We know what n is because it's a third order one, so we get our value to be 6.5 times 10 to the minus 7 meters. We then use speed equals frequency times by wavelength to then work out frequency, because we can say frequency is equal to 3 times 10 to the 8. We know that because it's laser light, so it's a light wave, divided by our value we've just worked out for lambda to get our answer to be 4.6 times 10 to the 14 hertz. Let's have a look at our next question. A student is provided with the following apparatus: a lamp, a polarizing filter, and a light meter that measures the intensity of incident light. Describe how the student could use this apparatus to determine whether the light coming from the lamp is polarized. So pause the video now, then unpause the video when you want to go through your answer. Right, now the first thing to note very importantly is that to observe if polarization takes place, you've got to be rotating your filter. So what you would need to have is you need to have a lamp on one side, a filter in the middle, and then the light meter on the other side of the filter. So that's our setup, which we can observe and monitor intensity during rotation. So as we rotate our filter around, if polarization is present, the intensity will vary, but it would not vary if it was not polarized. Now it's important to know that as it's rotated, you should see a maximum and minimum occur if you've got a polarized bit of light, because if the polarized light is in alignment with the filter, all of it should go through. But if it's 90 degrees out of alignment, you should get nothing going through. So you see your maximum and your minimum. Right, let's have a look at another question. So a progressive wave transfers energy along the wave, but stationary waves do not. So describe two other differences between stationary waves and progressive waves. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you answer this question? Now you've got to think of what the actual characteristics of stationary waves and progressive waves are. So you could say that stationary waves have nodes and antinodes while progressive waves don't. You could think that in a progressive wave the phase will vary continuously across all the points, but in a stationary wave all the points between the nodes which are next to each other are all in phase. Also, in a stationary wave, different points in your stationary wave have different amplitudes, but the point of a progressive wave is that all the points have the same amplitude because it's progressing through the substance. Let's have a look at our next question. A string of mass 0.98 grams vibrates between two fixed ends, x and y. The distance between x and y is 0.612 meters. The tension in the string is 69 newtons. Figure 1 here shows one position of the string when vibrating at the third harmonic. So use this to determine the frequency of the third harmonic. So pause the video now, then unpause the video when you want to go through your answer. Right, so with this equation we're going to be using the equation for a vibrating string, which is F is equal to 1 over 2L times by the square root of the tension over the mass per unit length. So you've got to now firstly work out what the mass per unit length is by doing the mass in kilograms divided by the length of the string in meters, which we are given both values, although we're given the value of mass in grams, but we can work it out in kilograms in the actual question. Now as well, it's important to note that because it's the third harmonic, okay, that when you've worked out your value for frequency in that equation, you've worked out the fundamental frequency. So to work out the frequency of the third harmonic, you've then got to multiply the frequency by 3, because the value you get in the equation F equals 1 over 2L times by the square root of T over mu, when mu is mass over length, that is going to be the frequency of the fundamental frequency, which is the base value there. So to work out your then harmonic, you then multiply by the harmonic number. So because it's the third harmonic, therefore it's going to be tripled. So the answer is going to be 509 or 510 hertz. Let's have a look at the next question. So figure 8 shows the apparatus a student uses to investigate stationary waves in a stretched spring. Two small pieces of adhesive tape are fixed to the string as markers P and Q. Markers P and Q are 0.55 meters apart and an equal distance from the ends of the string. A graph paper grid is placed behind the string between P and Q, and you'll notice that they're, like I said in this picture, they're 0.55 meters apart. So the string is made to vibrate at the second harmonic. So how would the motion of P compare with that of Q? So pause the video now, then unpause the video when you want to go through your answer. Right, so how can we consider this particular idea? You'll notice that P and Q are going to be in antiphase or completely out of phase. So our phase difference is therefore going to be pi radians. Now they will have similar amplitudes of vibration because they're in the same wave, okay, but so there'll be a similar displacement, okay, and they should have the same frequency and the same period, and they should again move with the same speed. Now it's important to know that if you're asked to describe about motion, you're asked to describe about wave properties of particular points, talk about the phase difference between the 2 points, but also compare your amplitudes, compare your frequencies, and compare your speeds. Let's have a look at the next question. The frequency of this vibration generator is then increased, and a higher harmonic of the stationary wave is formed. Figure 9 shows the string between P and Q at an instant in time. The dashed horizontal line indicates the position of the string at rest when the vibration generator is switched off. Now the frequency of the vibration generator is 250 Hz. Calculate the wave speed. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we've got to consider is as follows, that we want to use the equation V equals F lambda to work out what our value of V is. Now you can use this to determine what the wavelength is. Now you'll notice that between P and Q that this isn't actually one wavelength, it's actually two wavelengths between the two of them. Now you'll notice that because it's gone from a P to a peak and then from another peak to Q, which is the next peak along. So the distance between one wavelength is from peak to peak, or similar point to similar point on the next wave. So therefore it's going to be half of 0.55 meters, which is 0.275 meters. We know what our frequency is, it was given in the question. We multiply the two values and we get 69 meters per second. Again, that's an appropriate estimation, you would think, for the speed of a standing wave on a string. Let's have a look at our next question. The instantaneous position of the string in figure 9 can be explained by the superposition of two waves. The instantaneous position of these waves between P and Q is shown in figure 10. Describe the properties that the wave must have to form the shape shown in figure 9. So pause the video now, then unpause the video when you want to go through your answer. Right, so what's important to note here is that if you look at these two pictures, you'll notice that they have the same speed, however they're now moved in opposite directions, but they have the same wavelength or the same frequency, so you'd say they have the same amplitude. You know this because you can see that in the figure 10, that as a result here, they've got the same height, so therefore they must have the same amplitude, so we've got the same position as of our wavelengths, so we've got, as I said before, same wavelength, same frequency, similar amplitudes. Okay, they are got the same speed, but they are moving in opposite directions. Let's have a look at our next question. The frequency of the vibration generator is reduced until the first harmonic is observed in the string, as shown in figure 13. The string in figure 13 is replaced with one that has 9 times the mass per unit length of the original string. All other conditions are kept constant, including the frequency of the vibration generator and the tension in the string. Deduce the harmonic observed. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you tackle this particular question? Well, once again, you'll use the equation F is equal to 1 over 2L times by the square root of T over mu, where mu is the mass per unit length. So what you'll say is, if you have a look at this particular image, you know that mu has increased by 9. So therefore, when you work out your frequency, it's reduced to actually a third of the previous value, because what you've put in is you've put in mu to be 9 times as big, but it's square rooted, so 9 square rooted becomes 3, and because it's T over mu, therefore it's going to be 1 over 3. So therefore we can say that the frequency has reduced to a third of its previous value. So therefore the speed has reduced to a third of its previous value, so therefore the string must be being driven at 3 times this particular frequency to get this out. So therefore the harmonic which we're observing is going to be the third harmonic. Right, next question. In 1870, John Tyndall sent a beam of light along a stream of water. Figure 4 shows the modern version of Tyndall's experiment using a laser beam. Water has a refractive index of 1.33. Explain why the laser beam stays inside the stream of water. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've been given the refractive index and you've got to understand why it stays inside the stream of water. Now it's going to stay inside the stream of water because it must be carrying out total internal reflection, which is what you'll get 1 of your marks for. Now the second thing you've got to talk about is why it carries out total internal reflection. Now the important thing to note is the refractive index of water is 1.33. We know the refractive index of air, which is what's surrounding water, is 1. So you could say that the refractive index of water is greater than air, because that's actually a condition of total internal reflection, that to get that occurring, the refractive index of the material which carries out total internal reflection must be greater than that of the refractive index around it. Or you could say that the angle of incidence is greater than the critical angle, because that's the other condition which would allow for total internal reflection. Let's have a look at the next question. From the information given, calculate the speed of laser light in the water and calculate the critical angle for the water to air boundary. So pause the video now, then unpause the video when you want to go through your answers. Right, for this first one, what we've got to do is we've got to use the equation refractive index is equal to the speed of light over the speed in that particular material. Now what we know is we know that for water the refractive index is 1.33. We know that the speed of light in a vacuum is 3 times 10 to the 8, and so therefore we can work out the speed in the water by doing 3 times 10 to the 8 over 1.33. So we're now going to work out our value, which is 2.26 times 10 to the 8, and we give it to 3 significant figures. Why 3 significant figures? Because the information we've given in the question, the refractive index, was also given to 3 significant figures. Let's have a look at the next question. How do you calculate the critical angle for the water to air boundary? So you would work out your critical angle with your equation of sine critical angle is equal to 1 over n. So you can work it through like that. You've been given n, you work it through to get 49 degrees. Let's have a look at our next question. Tyndall's experiment led to the development of optical fibres, and figure 5 here shows a step index optical fibre. A step index indicating that there's multiple layers in your optical fibre. Discuss the properties of the step index optical fibre. So your answer should include the names of part x and y, a description of functions of x and y, and a discussion of the problems caused by material dispersion and modal dispersion and how these problems should be overcome. So pause this video now, then unpause the video when you want to go through your answer. Right, so for this one you've got to hit each bullet point individually to make sure you get your full 6 marks. So for the first bullet point, the name of X is the core and Y is the claddon. Now the function of the core is to propagate or guide the light, the wave, through the actual optical fibre by total internal reflection. Now what the properties you would need to know about for the core is it carries out low attenuation and low absorption, because I don't want it to take in any of the information from the light wave, and we need the refractive index of the core to be greater than the claddon, because for total internal reflection to occur, which is how the light will travel through the core, the actual core needs to have a refractive index greater than that of the material that surrounds it. Now Y, the claddon, prevents the core from damage. It prevents crosstalk between touching fibres, i.e. it stops the light waves going into different optical fibres and crossing over the information, and it also provides a clean, nice boundary for total internal reflection. Now the problems with modal and material dispersion are as follows. Both of them will cause pulse broadening and both of them will cause a limited bandwidth. Now material dispersion is caused because different wavelengths of the light will have different speeds, because they'll have different refractive indexes within the core. So that can only be overcome if you use a light of one wavelength. So you've got to send down a monochromatic, because the colour is the wavelength, beam for your information. Whilst modal dispersion takes place because if you've got a low critical angle which will carry out total internal reflection, that gives you multiple paths or modes for your light to totally internally reflect through the actual material. So therefore, that gives you different lengths, therefore different times, okay, that the actual waves are in the core, which can lead to the pulse broadening. So the idea is to do this, you've only got to allow a single mode fibre, only allow one possible pathway for the wave to totally internally reflect through. So that can be done by either having a narrow core, having a small refractive index between the core and the cladding, which would lead to a high critical angle, which would mean that there's fewer paths that the light could possibly take. Let's have a look at the next question. Scientists use optical fibres to monitor earthquakes. The light travelling through an optical fibre can be reflected by impurities in the fibre, as shown in the image. Earthquakes bend optical fibres slightly, and this changes the amount of reflected light. So suggest from the information why the amount of reflected light changes as the fibre bends. So pause the video now, then unpause the video when you want to go through your answer. Right, now there's a couple of different things you can talk about here. The first thing is that if it's now bent, the light can encounter impurities at different positions or angles, which will mean that it won't get through as much, or might get through more. The light can encounter a different number of impurities. It will encounter a different size of impurities because it's now taking a different pathway through the optical fibre. Again, interestingly, we said before that for total internal reflection to take place, your angle of incidence needs to become greater than your critical angle. Now the critical angle itself can't change because that's a property of the material, but the angle of incidence which the light will go through the core could change because of the earthquake, and if it's less than the critical angle you won't get total internal reflection. Bending might cause the cladding to crack, which would mean that you won't get all the total internal reflection because some light would seep out of the core because of this, and then you might say that the light actually may be refracted more, okay, than it was before because you need it for total internal reflection to actually go through your fibre optic cable. Now, the next question here shows apparatus used to investigate the stationary waves on a string. Now, the frequency of the vibration generator is adjusted until the first harmonic stationary wave is observed on the string, and you then repeat it for different loads. So, show how the frequency of F of the first harmonic is related to the tension in the string by the following equation. F squared is equal to 1 over 4 Lm times by T. So, pause the video now, then unpause the video when you want to go through your answer. Right, so how would you do this one? So what you've got to understand is that, like we said before, F is equal to 1 over 2L times by the square root of T over mu, where mu is mass over length. But it's important to note that here we're being given mass and length in the equation. So they want you to change mu in that equation to mass over length. So what you would do is you would square all the terms to get F squared, and therefore you pop in m over L for mu and rearrange it and get the equation which is written down there. The next question is, to measure the length of 2.600 meters, a meter ruler or a 5 meter measuring tape may be used. Both a meter ruler and a tape measure have a 1 millimeter resolution. Explain the advantage of using a 5 meter tape. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to think about what's going on here. Now, you think about that for the tape measure, there's actually going to be a smaller uncertainty for the tape measure because you're only having to use it once. Now, for a meter ruler, it's going to have a higher uncertainty because you're going to have to move your meter ruler multiple times to measure 2.600 meters, because your meter ruler, as you can imagine, is only 1 meter long, so you'd have to move it 3 times to actually measure 2.600 meters. So when you were moving that, there'll be a greater uncertainty in that, so therefore you would have a bigger error in your results. So you've got to consider that. Now again, this makes the key point that your uncertainty in your values isn't just the resolution of the measuring device, it's also the experimental technique of using that measuring device. Next question. The interference of light can be observed on the screen when a set of double slits is illuminated using a suitable light source. Figure 5 shows the interference pattern observed on the screen. Explain how the interference pattern shown in figure 5 is formed. So pause the video now, then unpause the video when you want to go through your answer. Right, so let's think about how we could get 3 marks here. Well, this is an interference pattern, so you've got to talk about how interference occurs. So you'd have the idea that there's diffraction going on in the slits. Now there must be diffraction in the slits because it's a double slit, and therefore you get superposition and coherence. Now you will get constructive interference, which causes the bright fringes. You get destructive interference that causes the dark fringes. Now you're then going to talk about path difference and phase difference and how they produce your bright and dark fringes. So it's the idea that if they're in phase, you'll get a bright fringe. If they're out of phase, you'll get a dark fringe. And then your path difference, if it's a odd number of half wavelengths between the two path differences between the two waves, you'll get a dark fringe. Whilst if it's an even number of half wavelengths between the two paths, between the two wavelengths, sorry, for your path difference, you'll get a bright fringe. You really need to learn how the phase difference and the path difference links to bright and dark fringes, constructive and destructive interference. Next question. The distance from the double slit to the screen is 3.5 meters. The spacing of the double slits is 7.3 times 10 to the minus 5 meters. Calculate the wavelength of the light used to illuminate the slits. So pause the video now, then unpause the video when you want to go through your answer. Right, so you can work out straight away what is going to be the fringe separation here. Well, you know the total distance between those is 0.24 meters, and between there you've got 8 fringes because you can count them. You can see how many there are. Now remember, you only count either the bright fringes or the dark fringes, so you get 8. So therefore, the fringe spacing is going to be 0.24 over 8, which is 0.03 meters. Now we know that lambda is equal to W, the fringe spacing, times by S, the slit separation, over the distance between the slit and the screen. So we've got all the other values and we pop in our W and we get lambda to be equal 6.3 times 10 to the minus 7 meters, which sounds about right because it's going to be laser light, so we're looking at that value of about 630 nanometers. Next question. Describe how you perform an experiment to make an accurate measurement of the wavelengths of monochromatic light. Your experiment should be based on the double slit interference technique and should discuss the choice of apparatus, the experimental setup, and how the apparatus is used. So pause the video now, then unpause the video when you want to go through your answer. Right, now once again, what you've got to think about is you've got to think about satisfying all the key points in this answer. So the first thing you've got to think about is you've got to think about a very basic method of what you could be doing. So what could you actually do here? So you talk about having your monochromatic light source, so it could be a light bulb which has a red filter from it or blue filter or whatever. You would then have your 2 slits, you then have your screen past your 2 slits. So you then got your very basic method of what you would do. So you turn on your light, you let the light go through the slits, and you would see the interference pattern form on the screen. Now what's very important is you've got to talk about all of the measurements that you would make. Now it's important to note that we want to be measuring W, we want to be measuring S, and we want to be measuring D. W being the fringe spacings, so you want to measure with the ruler the difference between the spacings on the screen formed, the slit separation, which you want to measure with the ruler between the 2 slits, and finally D, the distance between the slits and the screen, once again with the ruler, okay, measuring between the slits and the screen. Now again, you may think to yourself, what could you do in terms of which instruments you could use? Now you could use a meter ruler, I think, for the fringe spacings on the screen, a meter ruler measure the distance between the slit and the screen. You may say vernier caliper, traveller microscope for between the slits, because it's a very small distance to be measuring, so therefore you want a small percentage uncertainty in your actual measuring values. Then finally, you want to think how you would get your values accurately. Now firstly, you would talk about maybe measuring multiple fringes and then measuring and then dividing it by the value of the fringes like we did in the previous question to then work out the value, which will have a lower percentage uncertainty because you're measuring a bigger number. So instead of saying I'll measure the fringe space between 2 fringes, I'll measure between 10 and then divide by the value, okay, and then you can work it out like that. You could then have a laser which allows the value of D to be quite big because again you want the bigger the value, the lower the percentage uncertainty. So always think to yourself, A, how can I do a method to get accurate results? B, what values are going to measure and how am I going to measure them? What devices I'm going to use to measure them? And then finally, how can I make sure my values are as accurate as possible? And think about the practicals you've carried out in physics to do this. So, if we've been successful and learned in this revision session, you should be able to answer A-Level Physics examination style questions, assess your understanding on A-Level Physics, and understand what topics you need to improve upon for AQA A-Level Physics. So I hope you've enjoyed this revision session on waves, which is topic 2 for AQA A-Level Physics. Thank you very much for watching and have a lovely day.